Hello students, this is your friend Sumit and welcome to the topic 15 of this series, that is KTG and Thermodynamics. KTG and Thermodynamics are high weightage topic and we can expect almost 2 questions from these 2 chapters. For many of the students, KTG and Thermodynamics are very difficult topics, and trust me, after watching this one shot, you will feel very confident in these 2 topics and you will be able to solve any question on mains level, okay? Any question. So I'm going to discuss all the key concepts, all the theory, all the derivation in great detail, starting from very basic. Okay, even if you don't understand anything from these 2 topics, after watching this video, you will be grasp all the key points. Okay, and not only that, you will receive the practice sheets and the class notes also. So from the link that is given in the description, when you click that link, it will go to our app, and from there you'll join the free batch. You can access the notes, okay, for your revision and the DPP for your practice. So it is very important to do practice also, so make sure you do the practice. And if you talk about which of the subtopics are important from these 2, so from thermodynamics, I'll say understanding all the types of processes, how to find the work done, how to find the change in the internal energy, how to find the amount of the heat that is extracted or that is given to the gas. Okay, those type of questions are very important. And from KTG, different types of gas speeds and mixture of gases and mean free path concepts. Okay, so those things are very much asked. Anyways, we are going to discuss all the things of these 2 chapters in great detail. So let us begin the discussion. So let us begin our discussion. We'll be discussing 2 chapters, kinetic theory of gases and thermodynamics. So from kinetic theory of gases, first we will be talking about what all assumptions are there that are for ideal gas, then how we relate the microscopic properties to the macroscopic property of a gas, then different types of speeds, the ideal gas law, degree of freedom, mean free path, and then from thermodynamics, we'll be discussing about first law of thermodynamics, different types of thermodynamics properties, then second law of thermodynamics and Carnot engine. Okay, so let us quickly start our discussion. First of all, the assumptions. So these are the assumptions that are made for an ideal gas. Let us talk about them first. First of all, a given amount of gas is a mixture of very large number of identical molecules of the order of Avogadro number. So the number of molecules is very large. It's not that there are 100 or 1000 molecules, not like that. Next assumption is the molecules are moving randomly in all the directions. The motion is random. Next is at ordinary temperature and pressure, the size of the molecule is very small compared to the distance between them. It means if you talk about the volume, let us take, I am having a gas in a container. So the volume of container is very large as compared to the actual volume of the molecules. Okay, that is the assumption here. Then we have between them, thus the interaction between them is negligible, hence they move according to Newton's laws of motion. So that will be applicable there. Then the molecules do not exert any force of attraction or repulsion. It means there is no potential energy. Okay, there is no attraction or repulsion. If there is attraction and repulsion between the molecules, then there is potential energy associated with them, isn't it? Now, there is no interaction between the molecules. There is only kinetic energy that is associated with the molecule. So when we will talk about the internal energy, we will say internal energy only you can say constitutes of the kinetic energy, not of the potential energy, because there is no interaction between the molecules. Then we have the collisions of molecules against each other or within the wall of the container are perfectly elastic. There is no energy loss in that, such that the momentum and the kinetic energy of the molecules are conserved during collision, though the velocities change. Okay, so the collision is perfectly elastic. So if there is a collision with the wall of the container or between 2 molecules, that is perfectly elastic. So these are the assumptions. Now let us try to derive the pressure equation, okay, for a gas in terms of the speed of the gas, considering all these assumptions. Okay, so here basically what we are going to do is we are trying to relate the microscopic property, that is velocity, the momentum, the mass of particle, with the macroscopic property, that is pressure, volume, temperature of the gas, like that. Okay, so let us take a molecule, okay, one molecule whose velocity is v is equals to some Vx I cap, Vy j cap, Vz k cap. Let us take we are having this molecule, it is traveling with this speed. Now it collides with this surface that is A, B, C, D. Let us take, okay, this is that molecule, it collides. It was having some component along x-axis, some component of velocity along y-axis, some component of velocity along z-axis. Now it is colliding with this plane, okay, this plane. Now which component will get reversed? The x component. Other two components will remain the same. So it will collide, and after collision, the new velocities, let us take, this was the initial velocity. So after collision, the new velocity will be, the x component will get reversed. So minus Vx I cap, Vy j cap, Vz k cap. Okay, because the impulse is only along x-axis, so x component is getting reversed. Now if I ask you how much is the change in momentum of the particle, so you'll say change in momentum is equals to mass into change in velocity. So this will become minus 2 mvx, and this is along x, so I can write px. Okay, now a molecule came, collided, then went back, like that. Okay, so if I ask you in how much interval this collision was, so you'll divide with delta t. Delta t is the time it took the collision, like this is one collision, in how much time it will collide and then go back, and then again it will come. So total time it takes is, it is traveling 2l length along x-axis for one collision. Okay, after that then 2l length, then for another collision, like that. Okay, so along x-axis it is traveling 2l length, and in that time it is having one collision. So if I write delta t, so I'll say my delta t is basically, let me write here, so my delta t is basically the length 2l, I'm taking this as a cube of side l, so 2l divided by Vx. Let us divide it here. So divided by delta t, that is 2l by Vx. So Vx square it will become, this 2 is getting cancelled. So what it is, this is minus mvx square by l. What is this? Delta p by delta t, that is my force. Okay, this is the force due to this one particle. Okay, due to this one particle. Now if I ask you how much is the pressure, okay, so you'll say force divided by the area. Pressure is force divided by area. This much will be the pressure that will be contributed. Okay, that pressure there on this surface. So how much is that? That will become mvx square divided by area is l square into L here. What is L square into L? That is L cube. That becomes my volume. So this becomes minus m Vx square divided by, what is this? Volume. So this is pressure due to one molecule. Okay. Now if I ask you how much is the total pressure, so I'll say my total pressure due to all the molecules, let us take this was due to the velocity due to first molecule, okay, 1, then for second molecule also, for third, fourth, like that. So here minus m by v, and it will become v1x square plus v2x square plus v3x square, so on. Okay. Now what is this? This is, let me divide and multiply with n. There is n number of particles, like here. What is this? This is square, this is mean of the square. Okay, like we have root mean square, this is only mean square. Okay, so this is mean square velocity along x-axis. So I can write it as minus n m divided by volume, and this is Vx bar square. Okay, so this is mean square velocity along x-axis. Now if I ask you what is my RMS velocity, So RMS velocity, you will say that is v1x square plus v2x square plus v3x square, not x square, total velocity. So v1 square plus v2 square till vn square divided by n. This is my vrms square, you will say. Okay, now v1 is having vx, vy, vz. So v1x, v1y, v1z, like that. Okay, so when you open v1, so it will be v1x square plus v1y, I should write v1y square plus v1z square. So this is my v1. Okay, similarly it will be v2x square plus, like that, for v2, for v3, for v4, like that, divided by n. Okay, now taking all the x together, so what it will become, taking all the x together, only x. Let me take a different color here so that it will help you to visualize. Taking all the x together, so it will become v1 vx square. So v1x square plus v2x square plus v3x square till vnx square divided by n. That becomes the what it is? It is root mean square. So this is mean square velocity along x plus mean square velocity along y plus mean square velocity along z, like that. And due to randomness, I can say on an average these three are equal. So I can say my RMS square is basically 3 times of mean square velocity along x-axis. Okay, so this mean square velocity along x-axis, I can write it as VRMS divided by 3, VRMS square divided by 3. So this will become minus n m divided by v into VRMS square divided by 3. So this becomes my pressure. Okay, so let me have a dotted line, dashed line here. Okay, so I got my pressure. What is pressure now? Pressure is coming as minus n into m into VRMS square divided by 3V. From here, I can say that my PV comes out to be minus n into m VRMS square divided by 3. What is m? Mass of one molecule. What is n? Number of molecules. What is nm? Total mass. This is total mass. This is VRMS. If I take this 3 on the other side, divided by that by 2, what it will become? Okay, here there is a negative sign. I just need the magnitude, so don't consider it. Don't consider it. Don't consider it. Okay. Now, 3 by 2 PV. I took this 3, divide with 2, so this will become half n into m, that is my total mass, into VRMS square. What it is? Half total mass into velocity square, that is the kinetic energy. Yes, so this kinetic energy is coming out to be as 3 by 2 PV. Kinetic energy is coming out as 3 by 2 PV. Yes, so here this is important to remember. Okay, and we'll come back to this kinetic energy expression again. And when we will talk about the ideal gas law, that is PV is equals to nRT. Okay, we'll talk about that. PV is equals to nRT. From there, you can find the RMS velocity also, like PV is equals to nRT. So if I write here nRT and PV as nRT, from there you can write the expression of the VRMS, RMS velocity. So that is root 3 RT by m. We'll come to that anyways. Okay, now various types of speeds of gas molecule. Now there are so many molecules of the order of Avogadro number 6.022 into 10 to the power 23. Okay, of that order. Now is each molecule is having the same speed? No, that's not there. Each molecule is not having the same speed, so the speeds are different, and the speeds will be changing also, like the collision is there with the molecules, with the wall, okay, so the collisions are there and they are happening in a random way, so that speed will be changing, speed of a particle will be changing. But on an average, if you talk about how many number of particles is having this much speed, so that fraction is, I can say, almost that is constant. We will talk about that also, why that is so. Now we define different types of speeds. First of all, let us talk about the RMS speed. As this term RMS, R stand for root, S stand for M stand for mean, and S stand for square. So this is root, mean, square. So root, mean, square. So start from here. First square all the velocities, then take the mean of all the velocities, then take the root of that. That will become root mean square, as I mentioned. So what was that? Let us take different particles are there. First particle is having velocity v1, second is having v2, third is having v3. Okay, like that there are n number of particles. Now when I say root mean square, so first of all I'll square them. So square them. So v1 square, v2 square, v3 square, v4 square, v5 square, like that. Then take the mean, so add them, divided by the number of particles or the number of molecules. Okay, this becomes now mean. So square mean we did. Okay, so if this velocity, this is mean square. Now take the root of this. So take the root of this. Taking the root. So what it is now? This becomes my RMS velocity. This becomes my RMS velocity. Okay. Now let us derive that expression. So what we got? We got PV is equals to 1 by 3 mass of one molecule into number of molecules into VRMS square. We got this expression. Now from ideal gas law that we will derive in a while, I am using that here. So PV we know that is equals to nRT. Okay, so nRT is basically equals to 1 by 3 m into n into VRMS square. What is n? N is number of moles. What is that? So number of moles formula you can write in terms of mass also. So like the given mass divided by the molar mass, or you can write in terms of the number of molecules. So that is number of molecules divided by the Avogadro number. So you know that n is equals to the given mass divided by the molar mass, and this is equal to the number of molecules divided by the Avogadro number. Here this small m is mass of one particle, one molecule of the gas. Here this is the total given mass. Okay, so basically here this becomes my given mass. Okay, so if I write here n, so n is the given mass, so mass of one molecule into the number of molecules, so this is the given mass divided by the molar mass into RT, this is 1 by 3 mn into VRMS square, and from here this is getting cancelled and I am getting that my VRMS is equals to root of 3 RT by m. RMS velocity depends upon the temperature. Okay, it depends upon the temperature. If temperature is constant, RMS velocity will remain constant. Pressure is changing, doesn't matter. If temperature is constant, RMS velocity will remain constant. So mark this expression. Now can I write this expression in terms of P and V? Yeah. So we know that PV is equals to nRT. N is the given mass divided by the molar mass into RT. So now I can write it as P is equals to, this is given mass divided by volume, and this is RT divided by M. What is mass divided by volume? That is the density. So P is equals to rho RT by M. So RT by M I can replace as P by rho. Put it here. So this will become root of RT by M is P by rho. So 3P by rho. Let us write it properly. Rho. Rho is the density of the gas. Okay. Rho is the density of the gas. Now, I can also write this in terms of the Boltzmann constant. Now, this is root of 3 RT by M. Now, I know that Boltzmann constant is R by Na. Okay. So, this is, I'm getting 3 RT divided by M. Okay. Now, Boltzmann constant that we denote with Kb, what is that? That is R by Na. This, you know, this R is the universal gas constant and Na is the Avogadro number. So, R by Na. Now, if I use it here, so what it will become? This is the molar mass. So, this I can say as 3 RT. Molar mass is mass of 1 mole. That is mass of one particle into the Avogadro number. Mass of one particle or one molecule into the Avogadro number. Now this R by Na I can write as my Boltzmann constant. Okay, so it will become root of 3 kT by the mass of one molecule. This is molar mass. This is mass of one molecule. One molecule. Okay. Now here, wait a minute. Remember one expression. Remember in terms of RT by M. I remember it like this, root of 3 RT by M. I remember in terms of the molar mass and R. Now if I had to convert, I can quickly convert it. Okay, so 2-3 times if you do, you will remember others also. So at least remember one so that you are not confused. Remember one, 3 RT by M, that's all. Now this is my RMS speed. Next is the most probable speed. Let me write with a different color. Most probable speed. Now what is the meaning of most probable speed? We denote with VMP. Most probable speed means the speed which is possessed by highest number of molecules. Now each molecule is having different speed, we can say. So the speed which is possessed by highest number of molecules, the maximum number of molecules is having that particular speed. That is the most probable speed, we call that. Okay, and this most probable speed comes out to be root of 2 RT by M. Okay, I can write here possessed by maximum number of molecules. Now that is a root of 2 RT by M, and RT by M I can write as P by rho, so 2P by rho, or I can write as 2 into kT divided by the mass of one molecule. Any one of the expression you can remember? Okay, now the third is the average speed. It's not average speed of one particle, it's average of all. Okay, average of all. So v1 plus v2 plus v2, just add the magnitudes divided by n. So I can write this as v average. This is v1 plus v2 plus till vn divided by n. That is my v average, and this v average comes out to be root of 8 RT by pi into m. Okay, or RT by m you can write as p by rho. So this is 8 by pi into p by rho, or you can write RT by m as kT by the small m. So this is 8 by pi into the Boltzmann constant into temperature divided by the mass of one molecule. Now we are having these three speeds. First, we discussed about the RMS speed, then we discussed about the most probable speed, then the average speed. Many times, most of the times, if I say, if a question is asked that will be from RMS speed, this is the most important one. So almost you can say, you can take for 90% times. Okay, if a question is asked, that will be from RMS. But a question can be asked, what is the ratio of RMS and the most probable or the average, and which one is greater, which one is lesser. Okay, so if you take the ratio, okay, so let me write that. So V let us delete it. Okay, so let us write the ratio of RMS to, let us take average, to the most probable. Okay, so what is that ratio? So that was root 3 RT by m. Anyways, RT by m is common whole throughout. So that is root 3 is 2. Then we are having average. So that is root of 8 by pi. Then we are having root of 2. Okay, so here 3 is the greatest one. 8 by pi is in between. Okay, and then we are having 2. So VRMS is greater than V average, and that is greater than the most probable. And you can remember it like this. This is RMS, so this is R, and here we are having average A and M. R, A, M, Ram. Okay, name of Lord Ram. So here this is the sequence. R is the greatest one, A is in between, then we are having M. So this order is many times asked. Okay, find the ratio of the these three, or find the ratio of any of the two. So these type of questions are asked in mains. So keep this ratio in your mind. And let us discuss few of the questions. At which temperature the RMS velocity of a hydrogen molecule equal to that of oxygen molecule? Now velocity of hydrogen molecule, if I write, so root of 3 RT, what is the temperature? Which temperature? RMS, okay, temperature we need to find, divided by the mass of the hydrogen molecule, molar mass. What is the molar mass? So this is H2. Okay, so the molar mass is 2 grams. So it is root of 2 R 3 RT, sorry, 3 RT divided by 2 grams. We convert that to SI like this. Then we are having oxygen molecule. So VRMS, I'm writing, so take it RMS only. Okay, for O2, oxygen molecule. So what is that? Root of 3R into, what is the temperature there? So this is 47 degrees Celsius. So how much is 47 degrees Celsius into in Kelvin? Because SI is Kelvin, so we will convert that to Kelvin. So 273 plus 47. How much is this? 0 and 320. So this is 320. So put it here 320 divided by the molar mass. How much is that? 32 grams. So 32 grams means 10 to the power minus 3, like this. Okay, now both has to be equal, so equate that. So if I equate, anyways, 3 will get cancelled, r will get cancelled. Okay, so I'll get T divided by 2 is equal to 320 divided by 32. This becomes 10. From there I got the temperature of the hydrogen gas as 20 Kelvin. That is option D. So make sure when you write this formula, root of 3 RT by m, you take temperature in Kelvin and the molar mass in kg, not in grams. So we remember in grams, 32 grams. So don't just put 32, answer will be wrong. So put 32 into 10 to the power minus 3 always. Another question, consider a sample of oxygen behaving like an ideal gas at 300 Kelvin. The ratio of root mean square velocity to the average velocity of the gas molecule will be. So V RMS divided by V average. Anyways, temperature will get cancelled. So this ratio will not depend on the temperature. So what is RMS formula? Root of 3 RT by m. What is average formula? Root of 8 RT by pi m. M. So this RT by m part is getting cancelled. So what it is? Root of 3 pi by 8. 3 pi by 8. So as I was saying that these type of questions are asked, the order is asked, which one is the highest, then okay, so they will mention in the option like VRMS is greater than most probable, then greater than average, or average greater than most probable, greater than VRMS. So these type of options will be there, and then you need to mark one of them. Now let us talk about the gas laws. So the ideal gas law, PV is equals to nRT, how this was derived basically, that we will discuss here. So first of all, we'll talk about the Boyle's law, Charles' law, then Gay-Lussac's law, Avogadro's law, and Dalton's law of partial pressure. Now combining these, we are having our ideal gas law, which is PV is equals to nRT. Now how that was derived? From the kinetic theory, okay, in kinetic theory we discussed that PV was coming out to be 1 by 3 into Mn into VRMS square. So from that, how these are derived, and from these, how the ideal gas law, that is PV is equals to nRT, is derived. We will talk about that. So Boyle's law first. So Boyle's law is for when the temperature is constant first. Okay, so temperature is constant in this. So at constant temperature, Boyle's law states that the product of pressure into volume is constant. How that is constant? We got that PV is equals to 1 by 3 into M into N into VRMS square. Now VRMS square is proportional to temperature. This we discussed. This is proportional to temperature. So if temperature is constant, then what will happen? PV is equals to constant. If temperature is constant, this expression is constant. So PV is equals to constant. So the product of P into V is constant when the temperature is constant. And the curve, I can draw that PV curve here. Not the dotted one, solid. And let us take, this is my pressure, this is my volume, this curve comes out to be like this, a rectangular hyperbola. Okay. So let us take at a point the pressure is P1, volume is V1. At another point the pressure is P2, volume is V2. Okay. Here it is pressure is P1, volume is V1. Another point, pressure is P2, volume is V2. So we will say that my P1 V1 is equals to P2 V2, because the temperature is same. So this is our Boyle's law. Next, Charles' law. So it is when the pressure is constant, when pressure is constant. Now come to the same expression again. What was that? PV is equals to 1 by 3 m into n into V RMS square. If pressure is constant, if this is constant, VRMS is proportional to temperature, that is there. VRMS square is proportional to temperature. So if pressure is constant, I can say V by T is equals to constant. Okay, provided if pressure is constant. Pressure is constant. So the ratio of V by T, that will remain constant. This constant is not the same, okay. So that ratio V by T will remain the same. Now if I draw the curve V versus T, how it will look like? Let us take here is our volume, here is our temperature. How this will go? So V by T is constant, it will be a straight line that will be passing through origin, okay. So a straight line like this. Okay, when the pressure is constant. Now here, if I have, let us take 2 points here, the temperature is T1, the volume is V1, here the temperature is T2, the volume is V2. So I will say that V1 by T1 is equal to V2 divided by T2. Next is our Gay-Lussac's law. So it is when volume is constant. Now take volume is equals to constant. Now you may say, sir, PV is equals to nRT, so why you are saying it like this? PV is equals to nRT. If P is constant, we know V by T is constant. You know V by T is constant when P is constant from ideal gas law. We are deriving the ideal gas law from this. Okay. Therefore, we are not having ideal gas law first. We are having this expression first. From this expression, I am showing you this. Okay. That's the point here. Sometimes this is taught like, you know, PV is equals to nRT. So from here, so we call this Gay-Lussac's law. Not like that. Not like that. Okay. We are deriving the ideal gas law from all these. So volume is constant. If volume is constant, write the same expression again. PV is equals to 1 by 3 m n into V RMS square. Now here, if volume is constant, and we know that V RMS square is proportional to temperature, so P by T will remain constant. So if volume is constant, then what will be constant? P by T will be my constant. Again, draw that curve. Oh, let us take the same color. So here let us take pressure, here I am taking temperature. Now P by T is constant, so take a straight line here with this color, so it will pass like this, okay, passing through origin. Now if I have 2 points on this curve, let us take here the temperature is T1, the pressure is P1, here the temperature is T2, the pressure is P2, and here we are considering that my volume is constant. So I got the expression, what is P1 by T1 is equal to P2 by T2. Okay, I should highlight this basically. In previous one also I highlighted. Okay, let us highlight that. Here also let us do that. Okay. Next is Avogadro's law. So it states that if we are having two gases which are having the same pressure, they are having the same temperature, they are having the same volume, the number of molecules in both of them will be equal. Okay, so let us take, I am having one as hydrogen gas, another as oxygen gas. Both are having, you can say, let us take, I am putting them in the similar container. It means the volume is same, they are maintained at same temperature, they are having the same pressure. Then the number of molecules in hydrogen gas and in oxygen gas will be same. So this is our Avogadro's law. So I am having two gases. Let us take, this is gas A in a container. Okay, and this is gas B in another identical container which is having same volume. Okay, let us take, here the pressure is P, here also the pressure is P, here the volume is V, here also the volume is V, here the temperature is T, here also the temperature is T. Then number of molecules of gas A is equal to number of molecules of gas B. Okay, if these are the conditions, P, V and T are the same, Na has to be equal to Nb. This is Avogadro law. Now let us discuss about Dalton's law of partial pressure. So Dalton's law of partial pressure states that, let us take, I am having gas A and gas B in two containers, like this. Yeah, this is my gas A, this is gas B, here the volume is V, here the volume is V. Okay, and let us take, temperature is T, temperature is T. Here I am having the pressure PA and here I am having the pressure PB. Okay, number of molecules are different in both the gases. Now if I put these two gases in the same container, if I put these two gases in the same container having the same volume V, here the volume is V, and here I am having gas A plus gas B. In one container I put these two gases, then the pressure of this container will be equal to the individual pressures. This will be equal to the individual pressures. So the pressure of A plus the pressure of B, that will give us the total pressure here. You can show it like the total number of moles will be equal. If you use ideal gas equation, from there it comes like, okay, so I can just quickly show you roughly. So total number of moles will be N1 plus N2, N is equals to PV by RT. Okay, and here it is P1, volume is V only, RT, and this is pressure is P2 into V into RT. Okay, so pressure is basically coming out to be P1 plus P2. But we are not having ideal gas law first. Okay, I'm just showing you that it's the same thing actually coming from there. So from these, now combining all these laws, I got my ideal gas law. What is that? PV is equals to nRT. From there I am getting this. Therefore, I was not using this to show the proof of them. What is P? P is my pressure. What is V? V is my volume. N is the number of moles. R is the universal gas constant. And we know that R is equals to 8.31 in SI units. What is the basically SI unit? PV is having the unit of energy. Okay, so this is joules per Kelvin per mole. So joules per mole Kelvin. Okay, and here the temperature is in Kelvin. Okay, if you use this expression, the temperature is in Kelvin. Now I can change the form of this expression. I can write P is equals to number of moles as given mass divided by the molar mass. Okay, this becomes my density rho. Okay, so P becomes rho RT by M, isn't it? It's the same expression. Yes, it's the same expression. P is equals to rho RT by M, or I can write this expression in terms of the Boltzmann constant, as I was saying previously. Okay, how? I can write P into V is equals to N as my given mass divided by the molar mass, okay, into R into T. Now this what is that? Yeah, so this molar mass I can write as number of molecules into the mass of one molecule. Number of molecules into the mass of one molecule. Okay, okay, not like that, sorry. Let us write N as number of molecules divided by the Avogadro number. Yeah, from there we'll get that anyways. So R by Na will becomes our Boltzmann constant, and I got my PV is equals to N into K Boltzmann into the temperature. Okay, so yeah, this is how we can like change the form of the expression. Now K Boltzmann is my R by Na. What is R? 8.31. What is Na? 6.022 into 10 to the power 23. And if we solve it, it comes out to be 1.38 into 10 to the power minus 23. Okay, many times Boltzmann constant is given in the questions, or like we have to use that directly there. Let's solve some questions on this. Read it. The temperature of a gas having 2 into 10 to the power 25 molecules per cubic meter is at 1.3 atmosphere pressure is. Okay, what is the temperature? So I'll say that PV is equals to nRT, and I can write as N by Na into RT. So P comes out to be number of molecules per meter cube. It means I am given N by V. Number of molecules per meter cube. RT by Na, this will become Boltzmann constant into temperature. From there, I can write my temperature. Okay, what is temperature then? P divided by Boltzmann constant into my N by V. Is this expression fine? Yeah. Okay, now put the values. What is the pressure? Pressure is basically 1.3 atmosphere. So 1.38 into 1.013 into 10 to the power 5 Pascal. This is how I write 1 atm divided by Boltzmann constant is 1.38 and N by V. What is that? Sorry, Boltzmann constant is 1.38 into 10 to the power minus 23. Forgot that. Into N by V. What is that? 2 into 10 to the power 25. So 1.38, 10 to the power 23. This is 10 to the power 25. So 10 to the power 2 will remain. 10 to the power 2 and this 10 to the power 3 will remain there. So 10 to the power 3 is 1000 divided by 2. I'm taking this nearly as 1 only. Okay, 1000 divided by 2. What is 500? We got 500. I put everything. If we put everything in SI unit, the answer will also be in SI unit only. Okay, so this 500, it should be in Kelvin, not in degree Celsius. Okay, now here you may say PV is equals to nRT. The given things are not as per the formula directly. Okay, it's now you need to understand how we can write this term, molecules per meter cube. This is N by V. These type of things you have to think. Okay, because he can change, like the examiner can change the question accordingly. So you have to think which quantity it is actually. Now let us talk about the thermal coefficient of volume expansion for a gas. Now there may be different thermodynamic process. Okay, for a thermodynamic process, let us take PV is equals to constant, or let us take PV square is equals to constant, or P by V is equals to constant. So different type of thermodynamic process can be there. Now from there, if for a particular gas we have to find the thermal coefficient of expansion, how we can find? Now thermal coefficient of volume expansion basically relates the change in volume with the volume as delta V is equals to V into gamma into delta T. Okay, there we call that this gamma is the thermal coefficient of volume expansion, and that is delta V divided by V delta T. Okay, so this is basically our thermal coefficient of volume expansion. Now let us take some expression is given to you. PV expression is given. You can convert first that expression to VT, because I know I need only V and T relation. Some relation is given. Let us take PV square is constant. Let us take it as like this. Okay, I am giving you an example. PV square is equal to constant. Now convert this to T and V. So PV is equals to nRT. So 1 PV I can write as T. So it will become T into V as my constant. Everything else is constant. Now differentiate it. So I can write as delta T divided by T plus delta V divided by V, and this comes out to be 0. Okay, take log and differentiate the way we write the errors. Okay, so delta T by T plus delta V by V is equals to 0, and from there I can get my delta V by V. Delta V by V comes out to be minus delta T by T, and from there delta V by V delta T comes out to be minus 1 by T. So delta V by V delta T comes out to be minus 1 by T. So here this becomes my coefficient of volume expansion, thermal coefficient of volume expansion. Now any process is given, you can use the same method to find the thermal coefficient. Now questions are asked from this, therefore I am covering this. So here we see this question was asked in 2023. Let us read it out. The pressure and temperature T relationship of an ideal gas obeys equation P into T square is equals to constant. Okay, so PT square is equal to constant. Here the volume expansion coefficient of gas will be, so PT square is constant. Now I need only V and T, so pressure is proportional to T by V, so this will become T cube by V is equals to constant. Now if I differentiate it, so this will become 3 delta T by T minus delta V by V. This comes out to be 0, and from there I'll get delta V divided by V is equals to 3 delta T by T, and delta V by V delta T comes out to be 3 by T. So this becomes my thermal coefficient of volume expansion, 3 by T. Okay. Now let us talk about the two conditions, that is NTP and STP. Many times in the question it is mentioned that a gas is at NTP or is at STP. What is NTP and STP? So NTP is normal temperature pressure and STP is standard temperature pressure. So STP is our standard temperature pressure. Okay. So standard temperature and pressure. So what is the temperature at STP? So here the temperature is 0 degrees Celsius, or I can say 273 Kelvin, and the pressure is 1 atm. So at this condition, 1 mole of a gas will occupy 22.4 liter of volume. Okay. So 1 mole occupies 22.4 liter of volume at STP. Now talking about NTP. NTP stands for normal temperature pressure. So normal temperature pressure means here the temperature is 20 degrees Celsius. Okay, or 293 Kelvin. The pressure is 1 atm only. So here 1 mole of gas occupies 24 liters of volume. Okay, so these are the two conditions that are given in the question, therefore they are discussed, and we are discussing these things here. So in the question you may find a gas is at NTP, a gas is at STP. So there you need to understand what is NTP and what is STP. So now let us talk about the translational kinetic energy of gas. As we derived the formula, what was that? PV was equals to 1 by 3 mass of one molecule into number of molecules into VRMS square. Okay, now I can take this 3 here, divide with 2, so this will become half into the total mass into the VRMS square. So what is this? This is basically the kinetic energy. Which kinetic energy? Translational kinetic energy. Okay, here we are not considering the molecules having a rotational degree or like that. Okay, so only the translational kinetic energy. Translational kinetic energy. So this translational kinetic energy comes out to be 3 by 2 PV. Keep this formula in mind, that is 3 by 2 PV. So we can relate with the pressure of the gas and the volume of the gas. So if the pressure of the gas is P, volume is V, the kinetic energy comes out to be 3 by 2 times of PV. Let us discuss this question on this. The number of molecules in 1 liter of an ideal gas at 300 Kelvin and 2 atmosphere pressure with mean kinetic energy per molecule this. We need number of molecules. Now try to understand this. We know that PV is equals to 1 by 3 m into n into VRMS square. This is the total kinetic energy, half of m into n square, that is the total kinetic energy. Here mean kinetic energy, okay, means on an average the kinetic energy of one molecule he is talking about. If I write for one molecule, I'll take the number of molecules here, PV divided by the number of molecules, take 3 here, divide this with 2, so this is 1 by 2 m into VRMS square. So this is the kinetic energy now of one molecule. Directly also I would have said the total kinetic energy is 3 by 2 PV. For one molecule it will be 3 by 2 PV divided by the number of molecules. Okay, so this is given to us. This is given to us. What is that? This is this. From there what I need to find? The mean kinetic energy per molecule. Okay, what the number of molecules we need to find. So from there I can say the number of molecules is equals to 3 by 2 PV divided by the kinetic energy per molecule. Kinetic energy per molecule. Now temperature is given and the pressure is given to us. What it is given? The number of molecules in 1 liter of an ideal gas at 300 Kelvin and 2 atmosphere pressure. Okay, so here pressure and temperature is given, but I need PV there. So I can use PV is equals to nRT. PV is equals to my nRT. Okay, and this temperature is given to us. Okay, so from there the number of moles will come. How to relate that? How I can relate that? Anyways, let us write it as PV is equals to number of molecules divided by the Avogadro number into R into T. So I can write my what? PV is equals to N by Na into RT. If I write N by Na, anyways, N will get cancelled. Oh, the number of molecules in 1 liter. Okay, sorry, I did mistake. Volume is given. Here is the volume. So I missed that. So volume is given, pressure is given, temperature is also they are giving actually. But anyways, if they are giving, let us use that. So 3 by 2 into the pressure. What is the pressure? 2 atm. So I can just write 2 into 10 to the power 5 nearly. Okay. 2 atm I can nearly equal to 2 into 10 to the power 5 into volume. Volume is 1 liter. 1 liter is 10 to the power minus 3 meter cube. So 10 to the power minus 3 divided by kinetic energy per molecule, that is 2 into 10 to the power minus 9. Now this 2 is getting cancelled. 10 to the power minus 3, so this will become 10 to the power 6 in the numerator. So whole it will become 10 to the power 11. So this is 1.5 into 10 to the power 11 D. I think here data, extra data is there. Number of molecules is we need to find in 1 liter of an ideal gas. Volume is given to us, the temperature is given to us, the pressure is given to us. We can use PV is equals to nRT also here, isn't it? And from there we can find the number of moles, and from number of moles we can find number of molecules. So this kinetic energy is not needed. I don't know like if this data is correct or not. I don't know if we use PV is equals to nRT, we will get the same answer or not. You can check that and comment. But there is some extra data. Therefore I was confused, like if pressure and temperature is given and then volume is also given, then what is the use of the kinetic energy, mean kinetic energy there? That is not needed. PV is equals to nRT, everything is known. From there find the number of molecules, and from there I can say how many number of molecules are there from number of moles. Yeah, anyways. So sometimes what happens when extra data is there in a question, what happens is there can be like the mismatch, some mismatch can be there. I don't know that mismatch is there in this question or not, it can be there. So some mismatch can be there, like if you do by one method the answer will be different, if you do by the another method the answer will be different. Like sometimes like these type of silly mistakes happens from the setter side. Now let us talk about the Maxwell's law of distribution of velocities. So Maxwell law of distribution of velocity here suggests that like in a sample of a gas, each molecule, you can say large number of molecules are there, different speeds are there. So if we talk about speed of one molecule, that is changing. Okay, it collides, it changes in magnitude also. Okay, but if you talk about on an average, what is the fraction, how many, you can say what fraction of the molecule is having this particular speed, or what fraction of the molecule is having this particular speed. So that is almost constant, that is not changing. Now here we are having velocities of molecule, okay, and here we are having dN by dV. dN by dV means dN is the number of molecules molecules having speed between V and V plus dV. Okay, that many number of molecules is dn. So this is dn by dV versus V. Now the maximum number of molecules is having the most probable speed, isn't it? As I mentioned, most probable speed is the speed which is possessed by the maximum number of molecules. So maximum number of molecules here is having this particular speed for this curve. For this curve, maximum number of molecules is having this particular speed. So this is my most probable speed. For another temperature, this is the most probable speed. For another temperature, this is the most probable speed. And you see, as the temperature is increasing, the most probable speed is decreasing. Yeah, this is 2000, most probably is there. This is 1000, temperature is as temperature is decreasing, my most probable speed is also decreasing. I mentioned in the other way, I think I did a mistake, because we know V is equals to root 2 RT by M. If temperature will decrease, V will also decrease. Now this is 2000, if we go to 1000, this is 1000, most probable speed is lesser, isn't it? If you go to 500, the most probable speed is lesser. Okay, and if you integrate, if you find the area under this curve, let us take you find the area under this curve, what it will be? dn by dv into dv, integration of that will become just the integration of dl, that will give you the number of molecules. So total number of molecules is equal to the area under this curve. Now there is expression also of this curve, but you need not go into that much detail, that is not needed for us. Okay, so what is the expression though? So that is some complicated type of expression, that is not needed for us. So area under this curve will give us the number of molecules. Let me write it here. Area under this curve will give us number of molecules, because that is dn by dv into dv integration. Here we are having dn by dv. Now let us talk about the mean free path. So mean free path is the mean of the free path, means the mean of the distance between the two collisions. That is the meaning of mean free path. Now when a molecule is moving, let us take a molecule is there, it is moving. Okay, so in time t, it covers some distance. How much? V into t. In that distance, let us take, it has n number of collisions. So this is the total distance divided by the total number of collisions, that will become my mean free path. Total distance it covered divided by the total number of collisions it made while covering that distance, that will become my mean free path. Okay, so let me write mean free path is the total distance. So V into T, I am taking V average divided by the number of collisions. Now how to find number of collisions? Now this molecule will collide with any of the molecule which is from here to here. If any molecule is in between these two, okay, from here to here, so when it is covering, so this becomes a cylindrical kind of volume. So any molecule that will be inside this cylindrical volume will have a collision from this moving molecule. Okay, yes, okay. So how many collisions will be there? The number of molecules that are there inside this volume, this is V into T. This is the diameter of the molecule. Okay, so this total is twice of the diameter. So number of collisions n, which is my number of collisions, will be equal to the number of molecules inside this volume. Okay, I'm just writing or number of molecules inside this. Okay, so inside this volume, how many number of molecules will be inside this? We don't know. So let us take the number count is n. So n number of molecules are there in the space per unit volume. Okay, into this volume, how much is this volume? Pi r square h. Pi radius is d here. Pi d square into h is v into t. N is the number of molecules per unit volume. Okay, so coming back to the mean free path, put the things there. Mean free path, let us denote that with lambda. Okay, we denote this with lambda. So lambda will become equal to my v. V here, this v means the average speed only. So v into t divided by n. N is small n, pi d square v into t. So this vt is anyways getting cancelled. So this is 1 by n pi d square. Now this expression is not fully correct. There is a mistake in this. Can you tell? Pause this and in the comments mention what is the mistake. Okay, mention it. Now here the mistake is, I am considering only this molecule is moving, but other molecules will also be moving, isn't it? Yes. So you need to take the contribution of motion of the other molecules also. This is only I am considering here motion of only this molecule, but others are also moving. So there comes an additional factor of 1 by root 2 in this. Okay. So additional factor of 1 by root 2 will come here. Considering the motion of other molecules. As well. Therefore, lambda comes out to be 1 by root 2 pi d square n, and this is the formula that you need to remember. Don't remember this. Don't remember this. Let me mark also, like some of the students may see this and will think this is correct. So this is incorrect. Okay, this is incorrect. Now let us talk about the collision frequency. Collision frequency is 1 divided by the time period of one collision. How much will be the time period of one collision? So time will be the distance it covers divided by with the speed with which it moves. Okay, yeah. So what is lambda? Pi d square n. So this will become root 2 pi d square n and into the average speed. Average, when we write, we show these symbol, so don't get confused. What is this? Okay, so this means the average speed. Oh, average speed I am writing. This is average speed. Okay, just remember this formula only. Okay, from there you can relate it. So remember that lambda, the mean free path, is equals to 1 by root 2 pi d square n. Now n is number of molecules per unit volume. How this will change with pressure and volume? N is number of molecules per unit volume. So we know PV is equals to N by Na into RT. So number of molecules per unit volume is coming out to be P into Na divided by RT. So basically this is not number of moles, okay? So don't get confused. So this is number of molecules per unit volume. Let me write again here. The small n, number of molecules per unit volume. So it is basically proportional to pressure by temperature. Okay, everything is fine. Coming to some questions on this. Let us read it out. If the collision frequency of hydrogen molecule is in a closed chamber at 27 degrees Celsius is Z, then the collision frequency of the system at 127 degrees Celsius is. So here the temperature is changing. How the collision frequency will change? This is my collision frequency. Here we are having average speed. Now, yeah. Of the system changes at 27 degrees Celsius. Okay. Now here you see, this is a number of molecules per unit volume. Now number of molecules per unit volume depends on pressure and it depends upon temperature. Let me read the question again. Collision frequency of hydrogen molecules in a closed chamber is 27 degrees Celsius. Then collision frequency of the system at 120 degrees Celsius. Now closed chamber means the volume is constant. Volume is constant. If the volume is constant, number of molecules is also constant. Total, that is not changing. It means this small n is not changing due to the temperature. Okay, the small n is not changing due to the temperature because P by T is constant, pressure will automatically adjust that. Why I am saying volume is constant. Volume is constant, number of moles we take constant, okay, that is not changing, isn't it? So this n is constant. Only you can say temperature factor is coming in V average and that is proportional to root T. So I will say here F proportional to root of T for closed chamber. Okay, you can say for closed chamber. Got it how I am writing? F is equals to this formula I am writing root 2 pi d square n into V average. Now this is not changing, this will remain constant. This will change and that is proportional to root T. So F comes out to be proportional to root T. So initial frequency was Z, final frequency let us take Z dash. Initial temperature was 27 degrees Celsius, that is 300. Final temperature is 120 degrees Celsius, means that is 400. So from here I got my Z dash to be 2 by root 3 into Z. C option. Okay, now here can be a mistake from students thinking that number of molecules is inversely proportional to temperature, and if that is inversely proportional to temperature, a 1 by T factor will come here, root T factor will come here, so this will become 1 by root T. No, that will be wrong. As I am saying here, closed chamber, V is constant, N by V will remain constant. So that thing you need to keep in mind. Okay, another question. Calculate the value of mean free path lambda for oxygen molecules at temperature 27 degrees Celsius and pressure this. Okay, assume the molecular diameter is this. So temperature is given, pressure is given, molecular diameter is given. Use the mean free path formula. Lambda is equals to 1 by root 2 pi d square n. So basically I need first n. N is number of molecules per unit volume. Number of molecules per unit volume. This is my n, and what it is now, PNA by RT. Put it here. So lambda is equal to 1 by root 2 pi d square PNA by RT. Everything is fine. R by Na you can write as Boltzmann constant, because Boltzmann constant they are giving here. So you can write this as my Boltzmann constant into T divided by root 2 pi d square into P. Let me write it again. Root 2 into pi d square into P. Okay, now put the values. 1.38 into 10 to the power minus 23. This is my Boltzmann constant. What is the temperature? 27 degrees Celsius. So that is 300 Kelvin. 300 divided by root 2 is 1.414. 1.414 into pi is 3.14 into d square. What is d? D is 0.3 nanometer. So 3 angstrom. 3 angstrom square will become 9 into 10 to the power minus 20. Isn't it? Yeah. Angstrom is 10 to the power minus 10. So 3 into 10 to the power minus 10 becomes 9 into 10 to the power minus 20. Into the pressure. What is pressure? 1.01 into 10 to the power 5 Pascal. So write it as 1.01 into 10 to the power 5. Now do the calculation part yourself and mark your answer in the comments. So when you mention your answer, put the timeline, okay, and then write the option, so that I can see which question's answer you are talking about. Okay, now let us talk about degree of freedom. What is degree of freedom? So degree of freedom basically is the number of independent ways in which a molecule can possess energy. Okay, that is the meaning of degree of freedom. Number of independent ways in which the molecule can possess energy. Okay, so a molecule can have velocity along x-axis, velocity along y-axis, velocity along z-axis, and these three directions are independent from each other. Okay, so these are the translational degree of freedom. So these translational degree of freedom are three translational degree of freedom. Next is the rotational. So about which axis it can rotate. Let us take, it can rotate about x-axis, it can rotate about y-axis, or if it can rotate about z-axis also. Okay, so depending upon that, there will be number of rotational degree of freedom. Then comes vibrational degree of freedom. Now when vibration is happening means you can take like, this is a molecule, it is vibrating like this. Okay, so it is moving like this and this, so that is the vibration. So when vibration is happening, then you can say there will be kinetic energy also, there will be potential energy also of a molecule. Okay, we will talk about that in a while. So monoatomic gas can only have translational, yes, only translational degree of freedom, no rotational, because this is only one atom. Okay, so for monoatomic gas we are having 3 degrees of freedom. For diatomic gas translational will be there 3. Okay, now rotational. So here let us take, there are 2 molecules like this. So they can rotate about this axis, they can rotate about this axis. This is, you can say, like, you know, the axis coming out of the plane going into the plane. Okay, about this axis it's not there. Okay, so only about this axis and only about this axis this can rotate like this. So it means what? There are 2 independent ways. So we are having 2 rotational degree of freedom. So total degrees of freedom is 5 for diatomic. Now you may say, sir, what about the vibration? Vibration we generally don't consider at normal conditions, unless until they mention specifically that there are vibrational degree also. Okay, then only we consider. Generally we don't consider. One mode of vibration will have 2 corresponding, you can say, degrees for the kinetic energy also, for the potential energy also, because one mode of vibration means there will be kinetic energy of that vibration and there will be potential energy also of that vibration. But generally we don't consider unless until it is specifically mentioned. So don't consider vibration unless until it is specifically mentioned in the question. So only 5 degrees of freedom. Triatomic, here we are talking about linear, so 3 degrees of translational, and if it is a linear only, so only 2 rotational, one about this, like this. Okay, so only 2 rotational only, so 3 plus 2, here we are having only 5 degrees of freedom. If this is non-linear molecule, then we'll have 3 degrees of rotation also, one along x, one along y, one along z then. Okay, so there we will have total 6 degrees of freedom. Now Maxwell's law of equipartition of energy states that each degree of freedom has each degree of freedom contributes to half Boltzmann constant into T, this much kinetic energy for a molecule. Okay, so each degree of freedom will have this much energy associated with it, kinetic energy. Okay, it contributes of you can say their translational also, rotational also, whatever it is. Okay, if there are vibration also, accordingly you can consider that. So for each degree of freedom this much energy is there, half kT, where K is my Boltzmann constant. Anyways, let me write it R by Na because you get confused. Okay, this is my R by Na. This he is talking about for a molecule. Okay, each molecule, one molecule. Now if there are number of degrees are F, so is F is the number of degrees of freedom of a gas. So for each molecule, the kinetic energy associated will be how much? F into half K into T. Okay, for each molecule, the energy associated, you may write energy, or let me write kinetic energy. F by 2 into K into T. This is for each molecule. Now if I talk about for 1 mole, multiply that with Avogadro number. So Na, F 1 by 2 K into T into the Avogadro number. Boltzmann constant into Avogadro number will become R. So this is F by 2 RT. Initially, when I was talking about the kinetic theory of gases, I mentioned that we don't consider that an ideal gas has attraction or repulsion between the molecules. It means there is no associated potential energy of the molecules. There is only the kinetic energy that is associated with the molecules. It means if I say what is the internal energy of the gas, that means the kinetic energy of the gas. And what is the kinetic energy of the gas? That is F by 2 RT. So the internal energy of the gas, so the internal energy, let me write here only. So the internal energy of the gas, internal energy of the gas, that we denote with U, only constitutes of the kinetic energy. Okay, so that is the kinetic energy of gas. And how much is the kinetic energy for 1 mole? For 1 mole we got as F by 2 RT. This was the kinetic energy for 1 mole. So for n moles it will be n F by 2 RT. Okay, and this becomes the internal energy of the gas, where n is the number of moles. For n moles, the internal energy is n into F by 2 RT. Okay, so at any temperature, we say the internal energy of the gas is n into F by 2 RT. Let us discuss this question. A gas mixture constitutes of 2 moles of oxygen and 4 moles of neon at temperature T. Neglecting all vibrational modes, the total internal energy of the system will be, total internal energy will be internal energy of 1 plus of second gas. Okay, what is internal energy? N into F by 2 into RT. This is the formula. Okay, let me write here. U is equals to N into F by 2 into R into T. So for 2 moles of oxygen, so for oxygen I am writing, so this will be 2 into, what is the degree of freedom for oxygen gas? This is a diatomic gas. We are having 5 degrees of freedom. So 5 by 2 into R into T plus. Second is 4 moles of neon. So 4, number of moles is 4 into, for neon gas, how many degrees of freedom are there? 3 degrees of freedom. So 3 by 2 RT. Yeah, neon is a monoatomic. Yeah, okay, therefore 3 degrees of freedom. So from here, this 2, so 5 plus 6, we are having 11 RT. This becomes my total internal energy of the gas. Okay, is this fine? Yeah. Now, molar specific heat of gas. Molar specific heat of gas is the amount of heat needed for 1 mole of gas to change the temperature by 1 degree Celsius. Okay, so the amount of heat will represent heat with Q. Okay, amount of heat that needs to be given to 1 mole of gas to change its temperature by 1 degree Celsius. To change its temperature by 1 degree Celsius. Now you may say, sir, it depends on the process, isn't it? Like which type of process is there, because the heat will depend on that process. Like if the process is isobaric, if the process is adiabatic, if the process is, let us take isothermal, or like, you know, different types of processes are there. So the amount of heat will depend upon the process that is there. So different type of process means different types of molar specific heats. Getting it? So if we talk about, yeah, so this you got. So I can say that, let us take, if I'm having Q amount of heat I gave, and there were n moles of the gas. Okay, so Q is equals to n. Here molar heat capacity is C, delta T is there, the change in the temperature. So C is equals to the amount of heat per unit mole per unit change in temperature. Okay, so therefore I am saying C is the amount of heat that will be given for 1 mole of gas such that the change in temperature is 1 degree Celsius. So this is how we write it. So this is for a mole. Now sometimes the heat capacity is there, let us take like specific heat capacity. He's talking about per kg. Then that's a different thing. Don't get confused with that. Molar now specific heat capacity for molar heat capacity for different processes. So if process is different, the molar heat capacity will be different. So for now we will be talking about two types of processes. One is when the volume is constant. Okay, so when the volume is constant, the specific heat capacity there is, we represent that as CV. This is the molar heat capacity at constant volume. And then there is another at constant pressure that we denote with Cp, that is the molar heat capacity at constant pressure. So molar heat capacity at constant volume. Volume is constant. Volume is not changing. I am giving the heat to the gas. Where that heat will go? The gas will not expand or will not compress because the volume is constant. It means that heat what I will give will go to the internal energy of the gas. Will only go to the internal energy of the gas. What is the internal energy of the gas? NCVT. If the temperature changes by delta T, how much will be the change in the internal energy of the gas? That is NCV delta T. So if you give Q amount of heat, so that will be as NCV delta T. Okay, that will be NCV delta T, and this is the change in the internal energy because the gas is not doing any work, it's not expanding or it's not compressing. So my delta NCV delta T is equals to my delta U. Delta U is N into F by 2 into R into delta T. Okay, this is N CV delta T. From there I got my CV to be F by 2 into R. Next is when the pressure is constant. When the pressure is constant, we define the molar heat capacity as Cp. And this Cp is related with Cv as Cp minus Cv is equals to R. How this comes? We'll derive it in a while when we discuss in thermodynamics. Will come when then we will discuss about this. Okay. So as of now, just keep this like Cp minus Cv is equals to R. And the ratio of the Cp by Cv, that is my gamma, that is Cp by Cv, and this we call as the adiabatic constant. This gamma is the adiabatic constant. Okay, is that clear? Now let us relate gamma is equals to Cp by Cv, Cp minus Cv is equals to R, and Cv I got F by 2R. Wait a minute. Let us relate it. Like I got Cp minus Cv is equals to R,
and Cp by Cv, this is my gamma. So Cp is basically gamma into Cv. So if I put here, so gamma into Cv minus Cv is equals to R. From there Cv comes out to be R divided by gamma minus 1. Or from here I can say Cp, which is equals to gamma times of Cv, as gamma into R divided by gamma minus 1. Okay, remember these formulas in terms of gamma also. And this gamma is equals to Cp by Cv. Cp is Cv plus R divided by Cv. This is 1 plus R by Cv, which is Cv is equals to F by 2 into R. So this becomes 1 plus 2 by F. So I'm getting my gamma is equals to 1 plus 2 by F. So gamma is equals to 1 plus 2 by F, relating gamma with degree of freedom. Fine. Okay. Now here for monatomic gas, F is 3. So Cv is equals to F by 2R. 3 by 2R. Cp is Cv plus R. So 5 by 2. Gamma becomes 5 by 3. Ratio of the two. 5 by 2R divided by 3 by 2. So 5 by 3. For diatomic gas, F, the degrees of freedom is 5. So Cv will be F by 2R, 5 by 2R. 5 by 2R plus 1 will be plus R by Cp, that is 7 by 2. The ratio of the two becomes 7 by 5, that is 1 by 4. For triatomic, which is linear, so 5 here, this is 5 by 2, 7 by 2, 7 by 5, 1.4 only. Which are non-linear, here degrees of freedom is 6, so this will become 6 by 2R, which is my 3R. And Cp is equals to 3R plus R, that is my 4R. Gamma is 4 by 3, that is 1.33. Okay, so these things you should remember, keep that in mind, because this gamma for monatomic, diatomic or Cp, Cv, these things are needed. Now molar specific heat for mixture of gas. Let us take two gases are mixed. What will be the effective molar specific heat for the gases? Okay, now if I say the internal energy, that will be the sum of the internal energies of the two gases. What is the internal energy? That is N into N1 into F by 2. Let us take degree of freedom is F1 for this, into R, temperature is T, plus temperature is same in a mixture. Okay, so N2 into F2 by R. Okay, let me write in terms of Cv. So N1 into Cv1 into T plus N2 into Cv2 into T divided. Okay, this is my total internal energy. Yeah. Internal energy of first plus internal energy of second, and this becomes the effective formula for internal energy if I write. So N1 plus N2, these are the total number of moles, into C effective of Cv mixture. Okay, this is my Cv mixture, and the temperature is T. So T. From there I can say that T will get cancelled, and Cv mixture comes out to be N1 Cv1 plus N2 Cv2 divided by N1 plus N2. Okay, same way I can say my Cp mixture is equal to N1 into Cp1 plus N2 into Cp2 divided by N1 plus N2. And if you have to write the degrees of freedom, so in that way also you can write like this is F1 by 2R. Okay, here F2 by 2R, and here F mixture by 2R. So my F mixture, the degree of freedom of the mixture will come out as N1 into F1 plus N2 into F2 divided by N1 plus N2. So these formulas you can keep in mind. Okay, and let's take some gamma of mixture they are talking about. Then you may find Cv of mixture, from there Cp of the mixture, just do R. Okay, means Cp of the mixture certainly will be CV of the mixture plus R. Okay, and from there you can write what is gamma of the mixture. Let us see this question. N moles of a polyatomic gas, degree of freedom 6, must be mixed with 2 moles of monatomic gas so that mixture behaves as diatomic. Now, two ways I can say. Effective degree of freedom is equal to the degree of freedom of the diatomic gas, or I can say effectively the CV mixture will be equal to the CV of the diatomic gas, anything. So let me write CV mixture. So that is equals to N1 into CV1, N1 is N into CV1, degree of freedom is 6, so F by 2, 6 by 2 into R plus, this is fine, yeah, N1 into CV1 plus mixed with 2 moles of monatomic, so 2 into monatomic, monatomic means 3 degree of freedom divided by total number of moles, so that is N plus 2. What now, this behaves effectively like a diatomic, means this CV mixture is equals to the degree of, sorry, is equal to the CV of the diatomic gas. What is that? 5 by 2R. So this is my 5 by 2R. So write it, 5 by 2R is equals to, this becomes 3NR, this becomes 3NR plus this is 3R divided by N plus 2. R got cancelled, and what else? 5N plus 10 is equal to 6N plus 6. Yeah, so from there N comes out to be 4. Okay, so need not make a box here. N comes out to be 4. C. So these type of simple questions are there from mixture things. Another question we are having here. Consider a mixture of N moles of helium gas and 2N moles of oxygen gas. Okay, molecules taken to be rigid as an ideal gas. The Cp by Cv will be, means I need gamma. So let us find CV mixture first. So CV mixture is equals to N1 CV1 plus N2 CV2 divided by N1 plus N2. What is N1? N moles of helium gas. So N, it is a helium gas. Helium gas is a monoatomic gas. So the CV is 3 by 2R. So 3 by 2R. What is N2? N2 is 2N. What is second gas? That is oxygen gas. What is CV2? Oxygen is diatomic, so 5 by 2R. So 5 by 2R divided by N1 plus N2 is 2N plus N, that is 3N. So here N is getting cancelled. Okay, and what else? This is 3 and then 10 plus 3, 13 divided by 6. 10 plus 3, 13 divided by 6R. This is my CV mixture. Now CV mixture is equals to CV mixture plus R. What is that? 13 by 6R plus R. So what it will be? 19 by 6R. I got CV mixture, we need Cp by Cv, so that will become 19 by 13. 19 by 13. Simple questions are there. I want all of you to solve parallelly with me as I am solving these questions. So you may say, oh, it seems to be very easy. Sir is solving the questions very easily. But when you will solve these questions parallelly, then actually you will, have those points of doubts. Like sometimes when we see, we don't have those doubts. But when we try to write the equation and then we try to put the things, then we have doubt. Oh, what is this? What is this? Okay, which variable is this? How we need to mention this? How we need to put this value, that value? So then those doubts will come. Okay, so make sure when I am solving, parallelly you also solve. And also, like I have a good set of questions for you to practice, and that is there in the description. So when you will go in the description, click the link. So from there you go to the PW app, join the free batch there. In the free batch you will get these notes also and those set of questions also for your practice. When you practice those questions, you will get confidence. Okay, and also, if like let us take, you have to revise kinetic theory of gases, so all the formulas are there, all the derivations are there. So if you let us take have this PDF with you, quickly you can just go through, remember all the formulas very easily. Now we are starting thermodynamics. Now here basically we will be talking about gas. Okay, so this much amount of heat is given to the gas does this much amount of the work, and this much energy is you can say this much is the change in the internal energy of the gas. So these type of things will be talking in thermodynamics. So in thermodynamics we are having gas, and the states of the gas are defined by the pressure, volume and temperature of the gas. So here the gas is, let us take P1 pressure, volume V1 and the temperature T1, or sometimes the internal energy also U1, because we know that internal energy also depends on temperature. So the gas changes from this state to another state, okay, and that state again here pressure, volume, temperature or the internal energy. So this is the state of the gas. Okay, now this was initial state, this was the final state. So from initial state of the gas is changing like this. So the state of the gas, like in kinematics we define the position. So there we give the coordinates x, y, z like that. So here we give pressure, volume, temperature like that. Okay. So the state of the gas is defined by the pressure there, the volume there, the temperature there. So or the internal energy. Temperature and internal energy is similar, like internal energy is proportional to temperature. Now pressure, volume, temperature, these are the state functions or the state variables. These are my state variables. They do not depend upon the path, they depend upon the state there. Okay, doesn't matter which path you come at this. If you are coming here only, the state here will be this. Okay. Now some other variables, they are the path variables. Path variables like they depend upon the path, work done by the gas, how much heat is given to the gas or rejected by the gas. So those variables we call as the path variables. So in a thermodynamic process, a gas is going from initial state to the final state. Work done will depend upon how the gas is going. Okay, how you can say you are taking this gas from that state to another state. Is that process isobaric, or is that process isothermal, or is that process adiabatic, or is that process isochoric, or is that process polytropic, or there is some other type of process that you are defining there. Okay, so work done depends upon that, heat will depend upon that. So therefore we call them as the path variables. Now, when we will be discussing the thermodynamics, we will be talking about three types of systems. First is the open system. Second is the closed system. Third is the isolated system. Open system means it is open, like a container is there, gas is there, the container is open. Mass can be transferred, heat can be transferred, means energy can be transferred. Okay, so here we can transfer mass and energy both. Closed system means the container is closed, but you can transfer the heat from the walls of the container. You can heat the container from outside, yes. So only energy can be transferred. Isolated system means you cannot transfer anything. Okay, so no energy, no mass. Okay, nothing can be transferred. It's completely isolated. Getting it? So basically these three types of systems will be talking about. Now you may say, sir, let us take the gas is expanding or the gas is compressing in a process. Now the pressure in the gas, when we say, that is define the state of the gas. So how you can say during the process the pressure is same whole throughout? That's not possible, na? In a container you are having gas, you are compressing this container. So at all the points the pressure will be same inside the container? No, that will be different. But the process that we will be discussing will be taking quasi-static process. Quasi-static process means we are making the change very slowly. At each point equilibrium state is there. At each point pressure at all the points inside the container is same, or the temperature at all the points inside the container is same. So these type of process we call as the quasi-static process. So at each step there is equilibrium. Okay, so these processes are very, you can say quasi-static process means we are making the change very slowly. Okay, so the change is made slowly such that at each step or at each step of the process there is equilibrium. There is equilibrium. What does it mean? It means pressure is same, pressure or my temperature same whole throughout the gas, or the density also I can say, the density is same whole throughout the gas. Okay, density also you may write is same whole throughout the gas. Now let us talk about work done by an ideal gas. Let us take a gas as there kept inside a container. Okay, cylindrical container I am considering, and let us take, this is the piston of the container. Okay, the gas is there inside it, so just show dots like this. The gas is, let us take now, expanding. If the gas is expanding, it will be pushing this piston up. If I ask you how much work the gas will do, you may say, sir, we have learned the work done formula from work energy power, that work done is equals to integration of F dot dr. And let us take here that displacement is along x. Okay, here the force is F, so you will say thus it is integration of F dx. How much is this force? Force will be equals to the pressure inside into the area of the piston. Okay, A is the area of the piston, so this will become integration of pressure into area of the piston. What is AdX? AdX will be the change in the volume, that is dV. So this becomes integration of P dV. So the work done by the gas is given as W is equal to integration of P dV. Let us take here volume changes from initial volume V initial to final volume V final. Doesn't matter what is the process, the formula for the work done is integration of P dV. Now you may say, sir, but there are different formulas for work done for different processes. Yes, that is there. Why so? Because this integration will, like when you solve this integration, different expressions will come. Okay, but the general formula for the work done is integration of P dV, remember it. This is the general formula. Depending upon the process, if pressure is constant, we will take the pressure outside, then we will solve it. If the temperature is constant, accordingly we will write this expression. Okay, if let us take some other type of condition is given, then we will use that. Now what is integration of P dV? Integration of P dV will give you the area under the curve. Integration of P dV will give you the area under the curve. So let us take, you are having a PV curve. For a gas, this is pressure, this is volume, okay, and let us take some PV curve is maybe like this. Now if you want to find the work done by the gas, okay, not exactly like this, should not show zero volume of the gas. Okay, so let us take the PV curve is somewhat like this. Okay, from here A to B the gas is going. Now if you want to find the work done from A to B, how will you find? Just find the area under this curve. Okay, so this area will give you the work done. Okay, so now if the volume is increasing, the work done will be positive. If the volume is decreasing, the work done will be negative. Now work done, when we say done by whom, I am saying work done by the gas. This is work done by gas, I am saying. Now what is work done by the surrounding? That will be negative of the work done by the gas. Okay, so work done by surrounding is negative of work done by gas. Let me write it. Work done by gas. If gas is doing work, we consider that work to be positive. We will come to sign convention of the first law of thermodynamics. Then we will see that work done by the gas we consider as positive. Work done on the gas is considered as negative, like that. But anyways, till here you understand this. We'll come to that in a while. Now we are having this question. Okay. The thermodynamic system is taken through a cyclic process. The work done in the process is, now this is a cyclic process. Okay, you need the area under the curve. Now from this process, from C to D, the area is 0. From D to A, area is total this. From E to C, then negative of this area. So only the area here. So for cyclic process, when you are finding the work done, just take the area of the cycle. That's all. Area of the cycle will be the work done for the cyclic process. Okay. Area of the cycle. Now, if this cycle is clockwise, if the cycle is clockwise, it means the positive is greater, and when you are subtracting, that was lesser. So if the cycle is this clockwise, here P, here V, then this work done is positive. If this will be anti-clockwise, work done will be negative. Okay. So if this is clockwise, the work done is positive. If this is anti-clockwise, work done is negative. I'm considering P here and V here. If you reverse that, that will be different. Okay. Now let us solve this question. We need the work done. So area of this triangle. So 1 by 2 into the base. What is the base? Base is this 2 to 4. So that is 2 into height. How much is the height? Height is 100 to 400. So 300. Now this is 300 kilopascal. Okay, Pascal only. Yeah. This is 300 Pascal only, and this was meter. Both were in SI units. Okay. So what it is now? This is 300. What is the unit? Joules. 300 joules is the work done by the gas here. Work done in the process. Now, they are not saying whether this is work done on the system or work done on the gas or by the gas. By default, you may consider this is work done by the gas only. Specifically, otherwise specifically they mention sometimes. When there is positive negative signs are mentioned, so then they specifically mention this, that you need to mention that. Okay, the volume V of 1 mole of monatomic gas changes with temperature T according to the relation this, the work done when temperature changes by 90 Kelvin is XR, the value of X is. Now this is a polytropic process. We can do this question from the formula also of polytropic process work done. We will come to that. But here I am going to solve this from general method. Like we know that work done is equals to integration of P dV. From this I am going to solve it. Now, what is P? We know that PV is equals to nRT. V is given to us. So I can write P as nRT by V. nRT by V. Okay. But here change in temperature is given, so everything will take in terms of temperature. So we can write nRT by V, and V I can put here in terms of what? In terms of K and T. So K T to the power 3 by 2. So what it is? nR by K, and this will become T to the power, it was 3 by 2, 2 by 3. This was 2 by 3. So 2 by 3, 1 minus 2 by 3 is 1 by 3. 1 by 3 here. T to the power 1 by 3. Okay. Now that P I can put here. Also I need to write dV in terms of temperature. So V is K T to the power 2 by 3. So dV will be equal to differentiate it. So K 2 by 3 T to the power minus 1 by 3 dt. I just differentiated that. Now write everything. Integration of P. What is P? P is nR T to the power 1 by 3 by K into dV is K by 3 into 2 here T to the power minus 1 by 3 dt. T to the power 1 by 3 minus 1 by 3. K and K. So this becomes n 2 nr by 3, and that is constant, so that will come out. So 2 nr by 3, and integration of dt is t, and the limit will go from changes by temperature. The change in temperature is 90 degrees, so T1 to T2. T2 minus T1 is given as 90. And what is that is 1 mole. N is given as 1 mole. So right, so 2 by 3 into 1 into R into T2 minus T1, which is 90. So 30 into 2 is 60. So this is 60 R. X comes out to be 60. Okay. So this was the general method. Work done is integration of PdV. Any expression is given, I can write it like this. Now this is a polytropic process, and in polytropic process, when we'll come out, I'll tell you a direct formula also, like from there we will derive it, and from there also you can write. Okay, let us talk about the internal energy. Internal energy we already discussed, that internal energy only constitutes the kinetic energy of the gas only for ideal gas, and kinetic energy of the gas is given as F by 2 into R. F by 2 into RT for 1 mole. For n moles, we write internal energy as N into F by 2 into RT, or F by 2 R we know that is CV, so I can write it like this also, NCV into T. This is the internal energy. I'm just again writing it here, NCV into T. If the temperature changes by delta T, then we write the change in the internal energy as NCV into delta T. Now heat supplied. In a process, we supply some heat, and that we represent with Q. Now this is the heat that we are giving to the gas. Now it may happen that the gas is releasing the heat, then what it will be? Then if the gas is releasing the heat, we will say Q is negative. Okay, then sign will come positive or negative. And if there is a process in which there is no transfer of the heat, okay, the walls are, you can say, such that the heat cannot be transferred from the walls, then there what will happen? The Q will be 0. Okay, so depends upon the condition, or if there is some another type of process, let us take isochloric process is there. When volume is constant, how will you write? Heat given, you will say that is N CV delta T, because we know that is the molar heat capacity is C. Okay, so if the process is having molar heat capacity as C, so we say that the heat given is NC into delta T. Now C is the molar heat capacity of the gas. If temperature, if let us take, we discussed about volume only. Okay, so if volume is constant, Cp and Cv I'm talking about. Okay, if volume is constant, we'll use molar heat capacity at constant volume. If pressure is constant, we'll use molar heat capacity at constant pressure. If some other process is there, just find the molar heat capacity and put it. There you will get how much is the heat. Now first law of thermodynamics states that if we are giving a amount of heat Q to a gas, we are giving Q amount of heat to a gas, then this heat will be utilized in two ways. Okay, some part will go as the change in internal energy of the gas. Some you can say the kinetic energy of the gas will change. How? Temperature will change. Kinetic energy is related with temperature. Internal energy is related with the temperature of the gas. Temperature changes means the kinetic energy of the gas changes. So some part will go as the change in the internal energy of the gas, that is change in the kinetic energy as temperature changes. Another part will go as the work done by the gas. So some part will go as the work done by the gas. Let me write it here. Okay, so some part will go as work done by the gas, and some part will go as change in the internal energy. Energy of the gas. So this is some simple energy conservation. Total energy will remain constant, isn't it? Where it will go? It can go in two ways. So I can say that my heat given Q is equal to the work done by the gas plus the change in the internal energy of the gas. Here this is work done by the gas. Here this is heat supplied to the gas. Q is change in the internal energy of the gas. Change in internal energy of the gas. Now, if work is done on the gas, that work done will be taken as negative. If work is done by the gas, that will be taken as positive. So work done can be negative or positive. It will be negative when work done on the gas. It is when the compression happens. Compression is there. And it is positive when work is done by the gas. It is when expansion happens. Change in internal energy can be positive and can be negative depending upon the change in temperature. If temperature is increasing, change in internal energy will be positive. If it is decreasing, means it depends on the delta T. Delta U is NCV delta T. If delta T is positive, it will be positive. Delta T is negative, it will be negative. That's all. Okay. So my delta U is NCV delta T. So if delta T is positive, delta U is positive. Okay, it means if temperature increases, U increases. If temperature increases, delta U is positive. Same thing. If vice versa is there, it will be negative. Okay, so you can write it here. If delta T is negative, delta U is negative. Means if temperature decreases, delta U is negative. Now same for Q. If heat given to gas, we consider Q to be positive. If heat rejected by gas, it is rejected by gas, rejected or released, then this is negative. Okay, simple thing, like it's simple thing, like feel like, you know, conservation of the energy. You are giving some energy, that energy will be divided on two parts. Certainly it depends upon whether that is work done by the gas or work done on the gas, or temperature is increasing or temperature is decreasing, or whether the gas is accepting the energy or gas is releasing the energy. So the sign will depend on them. Coming to some questions on this. Okay, a monatomic gas performs a work Q by 4 where Q is heat supplied to it. The molar heat capacity of the gas will be dash R during the transformation, where R is, you know, universal gas constant. Okay, monatomic gas performs Q by 4 work. So first of all, Q is equals to W plus delta U. So Q is the amount of heat is supplied. Supplied means that I'll consider positive. Work is done. Here gas is performing the work, means gas is doing the work. So plus Q by 4 plus delta U. So from here I got my delta U as 3Q by 4. delta U as 3q by 4. Okay, the molar heat capacity of the gas will be. Now molar heat capacity, how to find? Write Q as Nc delta T. There C is my molar heat capacity, and I know that my delta U is equals to NCV delta T. Okay, so Q is Nc delta T and delta U, which is 3q by 4, that is NCV delta T. Take the ratio, N will get cancelled, delta T will get cancelled, Q will get cancelled. So this will become 4 by 3. So C is equals to 4 by 3 CV. Okay, so C is equals to 4 by 3 CV. So 4 by 3. And what is CV? This is a monoatomic gas. Monoatomic gas, CV is equals to 3R by 2. So this comes out to be 2R. This is 2R. Okay, is this clear? Fine. Moving ahead. The pressure of a gas changes linearly with volume from A to B as shown in the figure. If no heat is supplied or extracted from the gas, then change in internal energy of the gas will be. Means what? No heat is supplied or extracted from the gas means Q is equals to 0. Q is equals to W plus delta U. If Q is equals to 0, my delta U is equals to minus of the work done. Find the work done by the gas. Work done by the gas is equal to the area, this area, and volume is decreasing or increasing? Volume is decreasing. Work done by the gas is negative of this area. So work done, when I write, that will be negative of the area. How to write this area of this trapezium? 1 by 2 into sum of the parallel sides. This is 50 and this is 10, so that is 60 kilopascal. So into 10 to the power 3, sum of the parallel sides into the separation between the two. So that is 150 and this is centimeter per cube. Centimeter cube, sorry. This is 150 centimeter cube. So 150 into 10 to the power minus 6. How much is this? So 10 to the power 3, 4, 5. So 1 10 will remain in the denominator. 5 into 3 here, 5 into 2 and 2 into 3. 9 by 2. Minus 9 by 2. Minus 4.5 joules. So minus 4.5 joules is the work done. Delta U is minus of the work done. So my delta U comes out to be minus of minus 4.5. How much is this? 4.5 joules. Change in the internal energy. Now you see here, plus and minus, both options are there. Okay, and you can reject that simply by saying the volume is decreasing, work done is negative, work done is negative, change in internal energy will be positive, negative of that. Okay, Q is 0. Now let us talk about different types of thermodynamic processes. So one by one we will go. Let us talk first about isochoric process. Isochoric means volume remains constant. If the volume remains constant, then the work done will be, formula we know that W is equals to integration of P dV. Volume remains constant, this becomes 0. Okay, so work done is 0. If work done is 0, we know that Q is equals to delta U plus W. It means Q is equals to my delta U. and delta U is equals to NCV delta T. Okay, so this is there for the isothermal process. How the PV curve will look like? This is pressure, this is volume. So if volume is constant, it's not changing. So if the pressure is increasing, the curve will go like this. Okay, or if it is decreasing, it will come like this. Okay, so the curve will be somewhat like this. Volume is constant. And you may also draw the other curves also. You may draw even, let us take PT. This is my pressure and this is my temperature. If volume is constant, it means P by T is constant. If P by T is constant, it will be a straight line, and that straight line will be somewhat like this. Okay, let us change the color. Somewhat like this, you know. If you extend it, it will pass through the origin. Okay, so this is isochoric process. In isochoric process, work done by the gas is 0, and whatever heat you are giving, that goes as the change in the internal energy. 100% is going to the internal energy. No work is done by the gas. Now, second type of the process, let us talk about second type of the process, that is, let us take isobaric process. Isobaric process means my pressure is constant. If my pressure is constant, how will I write the work done? So we know that work done by the gas is equals to integration of P dV. If P is constant, I can take P out. This is integration of dV. Volume goes from V1 to V2. So this will become P into V2 minus V1, and this is P delta V. And if this is P delta V, PV2 I can write nRT2, PV1 I can write nRT1. So that will become nR delta T, isn't it? PV2 nRT2, PV1 nRT1. So this will become nR delta T. So this I can write this as nR delta T also. So for work for isothermal process, the work done formula is coming as either you can use P delta V or you can use as nR delta T. Isobaric process. Okay. Now, if I ask you how much is the heat given, how much is the change in the internal energy, so you can say Q, that is equals to delta U plus W. What is delta U? NCV delta T always. Why so? That is independent of the process. That is a state variable. So just write it as NCV delta T. Doesn't matter what is the process. It is always NCV delta T. Work done is nR delta T. This is my Q, and Q I can write as NC delta T, and this is isobaric, pressure is constant, so C is my Cp, so I can write as NCP delta T. And from here I got Cp is equals to Cv plus R. Previously I was talking about, and Q is my NCP delta T. Delta U is always NCV delta T. You may highlight if you want. In the previous also I wrote that. Yeah, here it is mentioned. Okay, and if you ask me, sir, how the PV curve will look like, let us do that. So let us take this as volume, this as my pressure. So this is P, this is V. Pressure is constant. If pressure is constant, the curve is somewhat like this, going like this. Pressure is constant. Okay, and if you want The other curve as well, you can draw that. Let us take V versus T. If pressure is constant, V by T is constant. If V by T is constant, it will be a straight line, somewhat like this, passing through origin, if you extend it. Okay, that's all about isobaric process. Now let us talk about isothermal process. Isothermal process means my temperature is constant, so T is constant. If temperature is constant, how we will write the work done? Let us take work done. The general formula we know, integration of PdV. Okay, PV is equals to nRT. Temperature is constant, I can write P as nRT by V. Replace it here. So this is integration of nRT by V dV. T is constant, nRT is constant, take that out. So this will become nRT V volume. This is 1 by V dV integration, that will become ln V. Volume is changing from V1 to V2, so this will become ln V2 by V1. This is log e to the base. If you convert that to 10 to the base, then there is 2.303 factor will come. 2.303 into nRT ln 10 to the base V2 by V1. This is how it will change. Okay. So work done is nRT ln V2 by V1. And if you ask me how much is the internal energy change, delta U is equals to NCV delta T. This is 0. So this is 0. So my delta U is 0 for isothermal process. Okay, delta U is 0 because delta T is 0. Now how much heat will be given? So Q is equal to delta U plus W. Delta U is 0, Q is equal to W. So Q is coming out to be equal to W. Let me write it again here. Okay, let me write it again here, otherwise you may get confused. So let me write again. Q is equal to W, and that is nRT ln V2 by V1. If instead of V1 and V2, the pressures are given to you P1 and P2, then what you can do? We know P1 V1 is equals to P2 V2. Because T is constant, my P1 V1 is equals to P2 V2. Let me write it here. P1 V1 is equals to P2 V2. So my V2 by V1 is equal to P1 by P2. So you can write in terms of pressure also. This is nRT ln P1 by P2. Okay. Now how the PV curve will look like, we have already discussed. Let us quickly draw that again. So we start from tail. Huh? Sometimes I confuse. So we start from tail. Let us take, this is P, this is V. PV is equals to constant. It will be a rectangular hyperbola like this. As the temperature will keep on increasing, this hyperbola will keep on moving away. Okay, let us take, this is at temperature T1, this is at temperature T2. Here my T2 is greater than T1. Because the product, P and V product is increasing, it should move up, isn't it? Yeah, common sense. Okay. And sometimes the slope of this curve is also asked. the P versus V, dP by dV. So PV is equals to constant. If you differentiate it, this will become dP by P plus dV by V. This is equals to 0. So dP by dV, this is coming out to be minus P by V. Slope of this curve. Okay, so this is my slope. Need not remember it, don't remember it, just see how to write it. And you can quickly write PV is equals to constant, differentiate it, and you can write it. So isothermal we discussed. Now we are going to discuss about adiabatic process. Adiabatic process. In adiabatic process, my Q is equal to 0. The heat supplied to the process is 0, and for this process, PV to the power gamma, this is constant. PV to the power gamma is constant. What is gamma? Gamma is my adiabatic constant, that is Cp by Cv. Okay. You can write in terms of temperature also. This will become Tv to the power gamma minus 1. That is constant. Okay, temperature and volume also you can write it. Anyways, any expression you can change. So temperature to the power gamma, temperature into volume to the power gamma minus 1 is constant because PV is equals to nRT. From there we can write it. Okay. Now Q is 0. We know that Q is equals to delta U plus W. If Q is 0, W is equals to minus delta U, and delta U is always NCV delta T minus NCV delta T. Okay. Now how the PV curve will look like? Now in this case, our PV curve is more steeper than the isothermal. Because gamma is greater than 1, it is more steeper than the isothermal. Okay, it goes somewhat like this. More steeper than isothermal. Gamma is greater than 1. If you try to find the slope of, let me write it here itself. So PV to the power gamma is constant. Here I can write as dP by P plus gamma dV by V, and this is constant, this is 0, I differentiated it. So from here dP by dV is equals to minus gamma times of P by V. Slope is greater. You see, in isothermal it was minus P by V, now it is minus gamma P by V. Gamma is greater than 1, it will become more steeper. Okay. Now polytropic process. Polytropic process, here we are having PV to the power alpha is equals to constant, where alpha is any, you can say, constant value. Okay, depend upon it, can be 1, it can be 2. If it is 1, it will become isothermal process, isn't it? Yeah. If it is 0, it will become isobaric process. It can be 2, it can be 3, minus 1, 2 by 3, anything. Okay. So PV to the power alpha is equals to constant, where alpha is my constant. Okay. So in polytropic process, if I ask you how much is the work done, then you need to integrate it, or what else? Yeah, then only you need to integrate it. Or if I ask you how much is the change in the internal energy, change in the internal energy is always NCV delta T, so that you can quickly write. But now let us write the work done expression, that is integration of P dV. P, let us take this constant as some constant K. I'm taking PV to the power alpha is my K. So P is K by V to the power alpha, isn't it? Yeah. dV integration. So K is constant, I'll take that out, V to the power minus alpha will go in the numerator. So if I integrate it, this will become V to the power minus alpha plus 1 divided by minus alpha plus 1. And K is PV to the power alpha. Here my, you can say, limit will come from initial volume V1 to V2. K is V to the power alpha, K is PV to the power alpha, taking that inside, it will become P into V, okay, it will become P into V, isn't it? PV to the power alpha, it will go inside, it will just become P into V, divided by 1 minus alpha. Pressure changes from P1 to P2, volume changes from V1 to V2, so this will become P2 V2 minus P1 V1 divided by 1 minus alpha. Okay, so work done comes out to be P2 V2 minus P1 V1 divided by 1 minus alpha, or PV is equals to nRT, so this is nR T2 minus T1 divided by 1 minus alpha. nRT T2 minus T1, you may write delta T, okay, so let me write it in simpler way, delta T. Fine. Okay, so work done, we got as this expression. Now if you see previously in adiabatic process, our work done was this, and what was CV? CV is R upon gamma minus 1, and you may write this as 1 minus gamma. Here in place of alpha we are having gamma, so this will become nR delta T divided by 1 minus gamma. Okay, I'm writing it as nR delta T divided by 1 minus gamma, or you can write in terms of P1 and P2 also. So this is P2 V2 minus P1 V1 divided by 1 minus gamma. You can write it like this. Okay, so I got my work done formula, and what is Q? Q is delta U plus W. Delta U is always NCV delta T. Work done is nR delta T divided by 1 minus alpha. CV is R upon gamma minus 1. So this becomes nR delta T into, or anyways, let me write it fully. So this will become n R by gamma minus 1 delta T. Okay, let us take n delta T, or delta T outside, n delta T outside, plus R upon 1 minus alpha into n this delta T. This is Q, and we can write this as NC delta T. From there, okay, one thing, you can keep this thing in mind, this expression in mind. Okay, from there you can write this as NC delta T. From there you will get the molar heat capacity for polytropic process, that is R upon gamma minus 1 plus R upon 1 minus alpha. Okay, so from there I got my C as R upon gamma minus 1 plus R upon 1 minus alpha, or you may write as minus R upon alpha minus 1. Anyways, this becomes the molar heat capacity for polytropic process, and this is required. This is asked. Okay, so this is polytropic process. Okay, coming to some questions. It was long discussion of all the processes. I hope you are able to understand nicely, because I was going step by step and explaining each point. So I am able to understand. I hope that you are able to understand each step here. Okay, if you understand each step here, it means your thermodynamics is clear. You can solve any question from thermodynamics. Okay. A hypothetical gas expands adiabatically such that its volume changes from 8 liter to 27 liters if the ratio of final pressure of the gas to the initial pressure of the gas is 16 by 81. The ratio of Cp by Cv means gamma it is asking. So Pv to the power gamma is constant. We know P1 V1 to the power gamma is equals to P2 into V2 to the power gamma. Volume is changing from 8 liters to 27, and the ratio of initial pressure to the final pressure P1 by P2 is 16 by 81. Initial to the ratio of final pressure to final pressure of the gas to the initial pressure. Oh, I did a mistake. I need P2 by P1. Yeah. P2 by P1 is equal to V1 by V2 to the power gamma. P2 by P1 is 16 by 81 and V1 by V2. It changes from 8 liter to 27 liters. So this ratio will remain the same, 8 by 27 gamma. Okay. Now, if you take 1 by 4, how we can reach it? How we can reach here? So this is 2 to the power 4. This is 3 to the power 4. And if you take 1 by 4th, this is 2 to the power, and here we are having 2 to the power 3 and 3 to the power 3 to the power gamma. So if I multiply here, if I make this power to be 4 by 3, isn't it we will reach here? Yes. So gamma comes out to be 4 by 3. Four by 3, this 3 will get cancelled. 2 to the power 4 by 3 to the power 4 will be there. Okay. Another question. At a certain temperature, the degrees of freedom per molecule of the gas is 8. The gas performs 150 joules of work when it expands under constant pressure. At constant pressure, it means this is our NR delta T. The amount of heat absorbed by the gas will be. Degree of freedom is 8. It means my CV is equals to, that is my F by 2R. So that is 4R. So delta U is equals to NCV delta T. Okay. What is 4 NR delta T. Yeah, 4 NR delta T. So what is Q? Q is equals to delta U plus W. Delta U is 4 NR delta T. This is NR delta T. So this is 5 NR delta T. What is NR delta T? NR delta T is 150. See, so this will become 5 into 150. This will become 750 joules. 750 joules. Yeah. Questions are simple from thermodynamics provided you understand the concepts very nicely. And thermodynamics weightage is, again I'll say, huge in mains as well as in advance. In advance, every year you will see questions will be there from thermodynamics. Okay. Another question, which of the following is an equivalent cyclic process corresponding to the thermodynamic cycle given in the figure? 1 to 2 is adiabatic. Okay, the options are here. So we need VT curve. So PV curve is given to us, we need VT curve. Let us draw it. Let us draw it. Which axis they are taking? V vertical, T horizontal. Okay. Now process 3 to 2 volume is, okay, 1 to 3 the volume is constant. 1 to 3 the volume is constant and temperature is higher at 1 because pressure is higher at 1. So temperature is higher at 1. So 1 to 3, so temperature is higher at 1. So this is 3, this is 1. Temperature is higher at 1, 1 to 3 the volume is constant, yes. 3 to 2 the pressure is constant. If pressure is constant, VT curve will be a straight line. 2 to 3, okay. So 2 to 3 the pressure is constant, that straight line will be passing through a region like this. Pressure is constant. So here my 2 process is going from 2 to 3, 2 to 3 and then 3 to 1, okay. And another, this 1 to 2 is adiabatic. So 1 to 2 is adiabatic, so that is PV to the power gamma is constant. If I write in terms of temperature and volume, that will become TV to the power gamma minus 1 is constant, okay. So it will be somewhat like this. Now let us come to the options. It is A is matching. Yeah, A is matching. Yes, A is matching perfectly. So these type of questions are very much asked in mains, and some PV curve is given, VT curve is asked, or PT curve is asked, or you know, like this. So, or they will give VT curve and they will ask PV curve. So these type of things are asked. So I am telling you the varieties of the questions. So you need to practice this, how to change, okay, how to understand which curve is that, which process is that, and how to draw that in the other variables, with other variables. Okay, another question, consider two containers A and B containing monoatomic gas at same pressure. Okay, two containers A and B, this is A, this is B. They are containing monoatomic gas at same pressure, volume and temperature. So P, V, T, P, V, T. A is compressed isothermally to 1/8 of its original volume. Compressed isothermally. Isothermally means temperature remains constant. Volume becomes V/8. So pressure will become 8 times because PV is constant. Pressure will become 8 times. Okay. While B is compressed adiabatically to 1/8 of its original volume. Here also the volume is V/8, but it is adiabatic. PV to the power gamma is constant. The ratio of final pressures. Okay, now here I am applying PV to the power gamma is constant. Okay, so P into V to the power gamma, this was the initial. Finally here pressure P, okay, let us take P 2, okay, into V. V is V/8 to the power gamma. What is gamma, by the way? This is monoatomic gas. Gamma is 5/3. Okay, Cp is 5R/2, Cv is 3R/2, 5/3. Write it as 5/3. 5/3. 5/3. This we got cancelled. P2 comes out to be 32 times of P. 8 to the power 5/3 is 32. So P2 is 32P. So the ratio of final pressures of B to that of A. So that is 32 divided by 8. So that is 4. D option. Okay. Another questions. Let us read it. A sample of gas at temperature T is adiabatically expanded to double its volume. Volume is changes to double. The adiabatic constant for the gas is 3/2. The work done by the gas in the process is adiabatic process. Work done is equals to, how to write work done? Adiabatic process. So work done is minus of delta U. So minus of delta U minus N CV delta T. That's all. Gamma is given 3/2. CV is R upon gamma minus 1. Initial temperature was T, final temperature we don't know. How to find that final temperature? Because I need delta T. So I can relate a temperature and volume. TV to the power gamma is constant. TV to the power gamma minus 1 is constant. Initial temperature is T, volume is V, gamma minus 1 is 1/2. Okay, because gamma is 3/2. Final temperature, let us take T2. Final volume is double its volume. So final volume is 2V to the power 1/2. So T2 comes out to be T by root 2. T2 comes out to be T by root 2. This is the work done. Now N is given, yeah, mole is 1. Put N is equals to 1, put gamma is equals to 3/2, so 3/2, so it will go 2 in the numerator. So this will become minus 2R into T by root 2 minus 1. So what it is? RT, you can take common, and a negative sign will be there, yes. And if you take 2 inside, root 2 minus 1. Or if you take negative sign, okay, let me write root 2 minus 2, sorry, not 1. Yeah, now it is fine. Root 2 minus 1 with a negative sign, so this will become 2 minus root 2. D option. Sometimes what happens, like when I'm let us say recording this video, so it's almost going to be 4 hours. How much is the time now? Okay, not 4 hours, now it's 3 hours. So mind becomes tired, so sometimes like it keep thinking what we have to do here. Okay, another question. The pressure and volume of an ideal gas are related as PV to the power 3/2 is constant. The work done when the gas is taken from state A to state B is, okay, PV to the power 3/2 is constant, so this is a polytropic process. For polytropic process, come to the equation of the work done. So work done is nR delta T upon 1 minus alpha. But here I think they are given pressures and volumes. So P2 V2 minus P1 V1 divided by 1 minus alpha. Put it here. P2 V2 minus P1 V1 upon 1 minus alpha. Now alpha is 3/2. So 1 minus 3/2 is minus 1/2. So minus 2 will go in the numerator. Okay, so I will say that is twice of P1 V1 minus P2 V2. Okay, yeah. Now here they are not mentioned work done, they just mentioned work done. Whether it is work done by the gas or work done by the surrounding, that should be mentioned specifically. But if it is not mentioned, generally we consider that is work done by the gas, generally. Okay, free expansion. Free expansion means the gas is expanding in free space. Vacuum is there. If free space is there, it means the work done by the gas is 0. in free space. Okay, now if some condition is given to you, let us take here there was a chamber, it is connected to another chamber, system is isolated, here there is a valve, okay, and let us take this, here it was gas and here it is free space, means vacuum. You open the valve, the gas expands like this, the system is isolated, work done is equals to 0, Q is equals to delta U plus W. System is isolated, so Q is also 0. Work done is 0, so delta U is 0 for these type of systems. Okay. Now let us talk about the cyclic process. Till now we discussed a little bit about the cyclic process. There I was saying that in cyclic process this is how we have to find the work. Okay, that only I discussed, nothing more than that. So let us take this cyclic process, P versus V. So cyclic process means you are starting from one state, the process will go somewhat and it will come back to the same state. Doesn't matter what type of process it is. Okay, so that will be given to you, given in the question. It may be a triangular thing, it may be a rectangular thing, or maybe a elliptical kind of path, depends. Okay, so mainly it is going from starting from initial state and coming back to the same state. Now in cyclic process, if I ask you how much is the total change in the internal energy, let us take this was state 1 going somewhat and then coming back. If I ask you how much is the total change in the internal energy, you will say that is 0. Why so? Because it is coming to the same temperature, same state is coming, delta T is 0. Therefore delta U is 0. If delta U is 0, if I write Q is equals to W plus delta U for the total process, let us take total process, this is 0, total Q net is equals to net work done. Q net means in some part it will be absorbing heat, in some part it will be releasing heat, but the total heat exchanged is equal to the total work done in the process. Sometime in a cyclic process efficiency is asked. Find the efficiency of the cycle. How we find the efficiency? We say efficiency is equals to how much it is the work done divided by how much heat is provided to the gas. Okay, so let us take in the process I am considering that Q1 is the amount of heat absorbed, and Q2 is the amount of heat released. So my total Q is basically Q1 minus Q2, and this is equal to the total work done in the process. And if I ask what is the efficiency, we will say efficiency is equals to work done divided by the heat absorbed. Okay, this is how we write work done divided by the heat absorbed. So work done is W divided by heat absorbed was Q1. For the cyclic process. Okay, let us discuss this question on this. A gas can be taken from A to B in two different processes, ACB and ADB. Okay, when path ACB is used, ACB, 60 joule of heat flows into the system. It means in ACB, Q is equals to 60. 30 joule of work is done by the system. W is equals to 30. So delta U is equals to Q minus W, that is 30. Okay. Now, if path ADB is used, work done by the system is 10 joules. Okay. The heat flow into the system in path ADB is, what is Q? I will say delta U will be the same because delta U is independent of the path. So delta U is 30. Q is equals to delta U plus W. So that is 30 plus 10. 40 joules. Okay. Is this clear? Now let us talk about reversible and irreversible process. Reversible process are those processes in which each step can be reversed. Okay. If let us take sorry. This is P versus V. Okay. So some process is going from state 1 to state 2 by some path like this. Now for reversible means you can exactly go back on the same path. Exactly you can go back on the same path. Okay. Which color? Let us take this. Okay. It means this is reversible. Now there can be irreversible process also in which you can go to the same state back but you cannot follow the same path. Okay, it's not, it may be some different path, maybe by this path it will go. It can go but it cannot go from the same path. Exactly it will not follow the same steps. Okay, so reversible means it can be exactly retraced. Reversible means it cannot be retraced. Irreversible means it cannot be retraced. Now let us talk about heat engine. So heat engine, like in heat engine we are giving some heat to the system. That heat is being converted to the work. Let us take an example of you can take an steam engine. Let us take. Okay, we are providing heat, so eventually steam is there and then steam is rotating the shaft like that. So you provided the heat. That heat is transferred to the mechanical work and some loss is there, means like that total energy cannot be converted to the output. Okay, so some loss will also be there, so some energy will go to the sink. So in this we have a source, we have a sink. Okay, we have a source at higher temperature, from there the system is taking the energy. We have a sink. Okay, so this is my source, this is at higher temperature T high, this is my sink, this is at temperature T low. Some heat is given. Okay, let us take this is Q1. From that some part is rejected to the sink, that is Q2, and in this process it does some mechanical work, that is my W, and from conservation I can say my W has to be equal to Q1 minus Q2. It's a representation of heat engine. Okay, it's not like heat engine will be like this. It's a representation of heat engine. Okay, so this is my heat engine. I can use, let us take this. Okay. So I gave some energy to the heat engine. From that, this engine did some mechanical work and some energy is released to the sink. Take an example of, let us take engine of a car. Okay, some fuel is burnt, so some heat is given, some mechanical work is done by that. Okay, wheels are rotating. Okay, some mechanical work is done and some energy goes to the sink, it is released as heat, like that. Now if here I ask you what is the efficiency, you will say efficiency is equals to the work done divided by the heat we provided. What is work done? Work done in terms of heat you can write as Q1 minus Q2 divided by Q1, and this is 1 minus Q2 by Q1. Okay, so this is our heat engine. Now second law of thermodynamics. Second law of thermodynamics states that it's not possible that whatever heat you are giving to the system will be fully transferred to the work. Now you may say, sir, try to make such a system such that total Q1 is coming here. No, Q2 becomes 0. So second law says that that is not possible. Okay, that is not possible. Ideal heat engine is not possible. And we are having another statement also. Ideal refrigerator is not possible. Means you can say a system cannot take heat from a source which is at lower temperature and give to you can say a sink which is at higher temperature. It cannot happen like that. Unless until you do some work. You can say sir, refrigerator is there, it is doing the same process, but we are doing some work on that, then only it is possible for it. Otherwise it cannot automatically take heat from the lower temperature and give to the higher temperature. Okay, so means the efficiency cannot be one. You may say, sir, if let us like only conservation law is there, only first law is there, the bottle should automatically jump from the table, cooling the surface of the table. Is that possible? You may say, yes, conservation of energy is there. The temperature, whatever energy was needed for the bottle to jump, that is provided from the heat as from the temperature from the table as heat. Okay, table is at lower temperature now, but it cannot happen automatically. That is the second law states. Okay, that cannot happen. Now, Carnot engine. Now, there can be different type of heat engine. In the process, you can take gas from different type of processes. Now, there is one particular type of engine, that is Carnot engine, that we call as the ideal engine. Means certainly ideal doesn't mean its efficiency will be 100. Means its efficiency is maximum. You cannot have another heat engine having efficiency greater than that under the same temperature conditions. Okay, so Carnot engine is the heat engine which is having the maximum efficiency working under same temperature, working under the two temperature. Let us take, this is pressure, this is volume. So Carnot engine consists of two isotherms and two adiabatic curves. So first of all, two isothermal therms like this. Okay, they are connected by two adiabatic. So yeah, okay, you can see here the two with the greater slope are adiabatic and two with the lesser slope are isothermal. So this is, you can say, isotherm. Okay, one isothermal, this is another isothermal, this is adiabatic, this is adiabatic. Let us take on upper isotherm, the temperature is T high, and on the lower the temperature is T low. Okay, let me write, and this is adiabatic, here I am writing This is adiabatic and this is adiabatic. This is isothermal. This is isothermal. So isothermal expansion, then adiabatic expansion, isothermal compression, then adiabatic compression. This is 1, this is 2, this is 3, this is 4. In adiabatic, there is no heat exchanged. Only isothermal process will have heat exchange. Let us take here the heat intake is Q1 and here it will release heat and that is Q2. Okay, now let us go step by step. Let us go step by step in process 1 to 2. This is isothermal. This is isothermal. I am considering P1 V1 volume at 1, P2 V2 volume at 2, P3 V3 volume at 3, P4 V4 volume at 4. Okay, volume pressure. Okay, so in isothermal 1 to 2, if I write the work done, what is that? nRT. T is T high, ln final volume V2 by initial volume V1. What is delta U? Delta U is W. Delta U is 0 because temperature is constant. Okay, and my Q is basically equals to W. Let us take this as my Q12. Q12 and Q12 is basically my Q1. This is my Q1 here then. Okay. Now let us talk about 2 to 3. This is adiabatic. Q23 is 0. Now work done if we write, what is that? In adiabatic process, work done is minus of delta U. Minus of delta U nRT ln. Sorry. NCV delta T. Now NCV delta T is CV we can write in terms of gamma. Okay. N CV is R upon gamma minus 1. Delta T. T low, final is T low minus T high. Okay. Now 3 to 4. 3 to 4. Yeah. 3 to 4. That is isothermal. Okay. If that is isothermal, then we can write here Q3. That is my Q2. Okay, basically, and that is equals to work done. Yeah, that is my Q2, and that is equals to my work done. How much is the work done? nRT ln V2 by V1. So nRT, T is T low, ln V2, V final is V4. So V4 by V3. nRT ln my V4 by V3. And V4 by V3 I can write as minus of V3 by V4. Because V3 is greater, therefore I wrote it like this. So heat is rejected. Now 1 to 4 to 1. Again this is adiabatic. Q is 0. What is the work done? I should name, okay. This work done was 1 to 2. 1 to 2. Then work done was 2 to 3. Then work done was 3 to 4. Then work done was 4 to 1. This is equals to minus of NR divided by gamma minus 1. Gamma minus 1 into final temperature minus initial temperature T high minus T low. Okay, what I am going to do is I am going to write the efficiency. Okay, what is the total work done? 1 2 2 3 3 4 4 1. 1 2 2 3 3 4 4 1. Now if you see W41 and W23, W41 and W23 are opposite of each other. Okay, so anyways they will get cancelled. Just add W12 and W34. What is W12? nRT high ln V2 by V1. And what is W34? Minus nRT ln V3 by V4. This was T low. This is my W net total. What is the heat given to the system? Q1. Q1 is this. T high ln V2 by V1. Okay, try to find the efficiency W by Q1. That is my efficiency. Okay. W by, if I divide this, first expression will get cancelled. So this will become 1 minus of that. Here NR will get cancelled. T low by T high into ln V3 by V4 divided by ln V2 by V1. V3 by V4 then V2 by V1. Is this correct? Yeah. Now let us relate V3 by V4 to V2 by V1. Now here you see, this is adiabatic, this is adiabatic. Now in process 2 to 3, this is adiabatic. I can say T V to the power gamma minus 1 is constant. Okay. So T V to the power gamma minus 1 is constant. So for this process 2 to 3, if I write T is at 2 is T high, there V is V2, 2 to the power gamma minus 1 is equals to, here the temperature is T low into V3 to the power gamma minus 1. Now same 1 and 4 I can use. So at 1 if I write T high into V1 to the power gamma minus 1 is equals to, at 4 T low into V4 to the power gamma minus 1, divide these two, and if you divide here, this is getting cancelled, this is getting cancelled, we are getting V2 by V1 is equals to V3 by V4. If that is there, this will get cancelled and I got my efficiency of the engine as 1 minus T low divided by T high. And this is the maximum possible efficiency. You cannot have a heat engine having greater efficiency than this acting between T high and T low. Okay. Yeah. Also, you can say here when we were saying efficiency, that was basically equals to my work done divided by my heat given. Work done was equals to heat taken, that is Q1 minus Q2, okay, divided by Q1. So this was 1 minus Q2 by Q1. 1 minus Q2 by Q1. We are getting the same thing. Okay, so basically Q is coming out to be proportional to the temperature. Okay, Q2 is at low, the heat that is related with the low sink temperature. Okay, so there you can write TL. Q1 is related with T high, so T high. That is basically proportional to that. Now coming to question. Let us read this. Let eta 1 is the efficiency of an engine at 447 degrees Celsius and 147 degree, while eta 2 is the efficiency at this and this. What is the ratio of eta 1 and eta 2? So eta is 1 minus T low divided by T high. So you now write eta 1 1 minus 447 and 147. So this is 147 is low. So 147 plus 273 divided by T high is 447 plus 273. Now eta 2 when you write, this is 1 minus. Final is 947 and 47. 47 is low. (947) is high. 947. From here you can do the calculations and you can find the ratio. I'm moving ahead. Now refrigerator. So refrigerator is what is doing? Refrigerator is taking heat from you can say sink. Basically sink means at lower temperature. It's taking heat from lower temperature and giving to heat to the higher temperature. This is what it does. Like the things which are inside the refrigerator, they are at lower temperature with respect to the surrounding. So from there you have to extract heat. So when it is possible? When you do some external work. Let us represent the refrigerator. So this I am taking T low. This is my T high. Okay. So this is low temperature. This is my high temperature. You are taking heat from low temperature and giving to the high temperature. Okay. For that we need to do some work here. Let us take, this is my Q2, this is my Q1. For that we need to do some work, and from conservation of energy we can say here that whatever heat is coming is equal to outgoing. So Q2 plus W is equals to Q1. So W is equals to Q1 minus Q2. Okay. Now if you write the efficiency, the efficiency will be equals to, now here wait a minute, here we don't define efficiency, here we define coefficient of performance, that is my beta. Okay, so that is coefficient of performance. So beta, here our interest is Q2. Interest is Q2. What we are doing is W. Q2 divided by W is Q1 minus Q2. Proportional to temperature, as I mentioned previously. Okay, this here, this is Carnot, but reversed Carnot. Okay. So here this Q1 Q2 will be proportional to the T1 T2. So Q2 is at lower temperature, so T low divided by, this is Q1, so T high minus T low. You can remember both of these things. Okay. Now let us do a question on this quickly. A refrigerator consumes an average 35 watt power to operate between minus 10 degrees Celsius and 25 degrees Celsius. If there is no loss, okay, that we know. How much average heat per second does it transfer? So Q2 divided by W, yeah. Q2 divided by W, what it was? T low divided by T high minus T low. And if you take in terms of dq by dt, this ratio will be there. Okay. Yeah. Now dq by 2 by dt we need. This is our interest, and dw by dt is 35. Okay, this is what it is consuming. So from here, if I write dq2 by dt, this is basically, sorry, this is basically dw by dt into my T low. T low is, what is T low? This is this, minus 10 degrees Celsius. Convert that to Kelvin. So 263 Kelvin, yeah, divided by difference. You have to take difference is 35, and dw by dt is 35. Sorry, this was multiplication here, not equal to. This was multiplication. This was 35. This got cancelled. We got dq2 by dt as 263 watt. Yeah, 263 watt. Perfect. Okay. Yeah. So this was about thermodynamics and kinetic theory of gases. A bit long video, but certainly I tried to cover everything. Everything means everything, all the key concept, every derivation I have considered here, and with that, what type of questions is asked. So again and again I was saying, like, this type of question is asked, this type of question is asked, prepare for this, that. So if you have skipped any part of this video, make sure you go and watch that again, okay, because this will help you a lot. When I'm saying that this type of questions are asked, so it means there is more chances that they can be asked again in 2026 as well. So make sure you watch each and every part of this video fully, and yes, with that, do some practice from the link that is given in the description. So don't miss the practice. Practice is must. You have seen me, you have solved some of the questions with me, now practice yourself. And also, if this video has helped you in any way, make sure you leave a positive comment so that I get motivated to put some more videos like this. So thank you all, have a nice day.